Hello there and welcome to Life Beyond Seen, where curiosity settles in, questions unfold at an easy pace, and science becomes something you can rest alongside rather than wrestle with. Tonight we're sinking slowly, calmly, into one of the most unreachable places on Earth. A place so distant from our daily experience that it might as well be on another planet, and yet it sits quietly beneath the same oceans we walk beside on warm afternoons. We're drifting toward the Challenger Deep, the lowest known point in the world's oceans, a trench so remote and so unwelcoming that even our most ambitious machines struggle to stay whole in its presence. As strange as it might sound, there's a kind of comfort in approaching something so far from anything we can touch. It gives us room to think, to feel a bit smaller in a way that's not frightening but rather grounding, a reminder that the world is larger than our routines and screens and everyday concerns, and while we'll keep a gentle pace, there's plenty to explore about why this hidden world remains, in many ways, beyond our true reach. Before we start drifting downward, I'd love to know where you're listening from tonight. Are you near the coast or somewhere far from the sea? Is it daylight where you are, or are you settling in under the quiet of night? It's always interesting how we gather in these different places and times, yet meet in the same moment, sharing the same descent into ideas that stretch well beyond the familiar. And if you enjoy these slower journeys, if they help you unwind or learn something new while keeping the world at an easy distance, I'd be grateful if you gave the video a like or maybe subscribed. It helps this little space stay tucked away but still reachable for anyone who might need a calm corner to settle into. Now, the Challenger Deep is one of those subjects that invites a kind of quiet awe. Not the loud kind that comes from fireworks or dramatic discoveries, but the kind that comes from realizing there are still places on our own planet that don't cooperate with our desire to explore and measure and map everything we lay eyes on. It's a reminder that nature still keeps some of its pages sealed, not out of malice or mystery, but simply because its conditions don't bend to what human bodies or machinery can tolerate. As we begin this slow descent, it's helpful to imagine not some grand expedition, but something much simpler. Picture standing at the shoreline, watching the waves roll in and out, feeling how gentle the ocean seems from where you stand. It's easy to forget that beneath those calm surfaces are layers of darkness, pressure, and cold that grow more intense with every meter downward. We think of the sea as familiar, something we swim in or sail across, but the truth is that most of it remains profoundly inaccessible. The deeper we go, the more the world we know begins to fade. Light disappears surprisingly fast, swallowed by the water long before we've even left the upper layers. What feels bright and open near the surface becomes dim, then shadowed, then entirely dark. And while that shift might sound dramatic, it's less like flipping a switch and more like the slow closing of a curtain, quiet and incremental. By the time the last hints of sunlight vanish, we're nowhere near the depth where the Challenger Deep waits. Most of the ocean is already out of sight long before we reach even a fraction of what lies downward. This gradual disappearance of the world we recognize is just the first sign of why exploring the deepest point of the ocean remains so difficult. Our senses simply aren't built for environments that strip away light, warmth, and movement in the ways the deep sea does. As we sink further, the pressure increases. This isn't the ordinary pressure you feel in your ears during a dive or a plane landing, but an overwhelming force that builds steadily, relentlessly, without pause. At the surface, pressure is something we barely think about, but for every 10 meters we descend, the weight of the water above grows by another full atmosphere. This means that by the time we've gone down even a few hundred meters, the pressure is already dozens of times stronger than anything we feel on land. It pushes from all directions, squeezing anything not built to withstand it, and we still have thousands of meters to go before we reach the deepest trenches. The Challenger Deep sits nearly 11 kilometers beneath the surface, a distance that might not sound extraordinary until you consider what it means physically. The pressure there is more than 1,000 times what we experience at sea level. It's enough to crush steel, distort titanium, and collapse any hollow space that isn't reinforced with meticulous engineering. Even the machines specifically designed to survive at those depths return from the journey showing the toll the environment has taken on them. Humans, of course, cannot survive this pressure at all. Our bodies are full of air spaces, tissues, fluids, and delicate structures that depend on a certain balance to function. Even a slight increase in pressure can cause discomfort, and a large one can cause injuries. At the depths we're drifting toward, survival without protection is impossible. We rely entirely on submersibles, remotely operated vehicles, and pressure-resistant materials to make the journey. And even then, these machines must be shaped, sealed, and reinforced with incredible precision. The smallest flaw can become a catastrophic failure. That fragility is part of what makes the Challenger Deep so unreachable. It's not that we lack curiosity or courage, it's that the environment doesn't offer any compromise. It doesn't meet us halfway. It simply exists the way it does, unbothered by whether we can enter it or not. Temperature also drops as we descend, but not in a dramatic storybook way. The shift is steady and predictable, cooling the water until it reaches near freezing. It's not cold in the sense we feel when we step outside on a winter morning, because the cold here doesn't sting or bite. Instead, it wraps around everything like a constant uniform chill, one that never eases no matter how much time passes. This cold, combined with the absence of light and the crushing pressure, creates conditions unlike anywhere we can visit on land. Machines must be insulated not just against pressure, but against temperature changes that can warp materials or affect electronics. Batteries drain faster in the cold. Mechanical parts behave differently. Materials that are flexible near the surface become brittle. All of this adds layers of complexity to exploration even before we consider what we might want to do once we reach the bottom. Communication also becomes a problem the farther we descend. Radio waves don't travel well through water, and light doesn't reach far either. That means any signals we send or receive must rely on sound, which travels well underwater but carries limitations of its own. Sound moves slowly compared to radio signals, and messages can become distorted or delayed. A remotely operated vehicle in the Challenger Deep doesn't respond instantly to commands. Everything feels slower, more uncertain. If something goes wrong, the delay can mean the difference between retrieving a machine intact or losing it forever. And losing a device at those depths is not like dropping something in a lake or misplacing a tool. It's gone for good, swallowed by a place we cannot simply dive into to retrieve what we've lost. Even when we imagine building something stronger, more resilient, more advanced, we run into limits set not by a lack of ambition, but by physics itself. Pressure-resistant materials can only be made so thick before they become too heavy to lift, too unwieldy to maneuver, or too dense to remain buoyant. Electronics can only tolerate so much cold before they fail. Structural supports can only counter so much force before they deform, and every new layer of protection adds weight, complexity, and cost. The deeper we go, the more the environment fights back, not intentionally, but simply by existing in a state that does not welcome our presence. Explorers often compare it to space, but even that comparison is imperfect. Space is hostile, but it's mostly empty. The deep ocean is hostile because it is full of pressure, full of cold, full of water that presses on every surface at all times. Despite these challenges, we've sent a small number of missions to the bottom. Submersibles shaped like reinforced capsules, robotic vehicles insulated against the extreme cold, and equipment designed to withstand pressures most materials cannot approach. Some have succeeded, others have failed. Every success offers a brief glimpse into a world very few have seen, but these glimpses are fleeting. The machines must return quickly. Human-piloted expeditions require careful planning, precise construction, and an understanding that even with the best engineering available, the environment leaves no room for mistakes. And even when everything goes right, the time spent at the bottom is limited. The descent alone takes hours. The ascent takes just as long. The window of exploration is small, constrained by battery life, safety limits, and the limitations of life support systems. It's not like visiting a place on land where you can stay as long as you want, walk around, observe freely, and adjust to your surroundings. You arrive, gather what information you can, and leave before the environment, the equipment, or your own physiology makes further time untenable. For all these reasons, the Challenger Deep remains not just unexplored, but largely unapproachable. It's not that humans haven't tried to unlock its secrets. It's that the forces at play resist our efforts in ways we can't negotiate with or bypass. There's a quiet acceptance in knowing that some places are simply beyond our reach, not because they're hidden, but because they are shaped by conditions that don't align with what human bodies or human technology can manage. As we continue sinking in this gentle journey, the reality of why we can't truly explore the Challenger Deep becomes clearer, but we're only beginning to touch the surface of everything that contributes to its inaccessibility. The pull of the deep has been with us far longer than any map, any instrument, or any technology that could help us understand what waits below. Long before we could measure depth or chart the ocean floor, people stood on shorelines looking out at the open water, feeling something they couldn't quite name. It wasn't fear, not entirely, though the sea has always earned a certain level of respect. It wasn't only curiosity either. It was something in between, a sense that the ocean held answers or possibilities, or simply a kind of stillness that you couldn't find anywhere else. Even now, with satellites and sensors and remotely operated vehicles, that feeling hasn't changed. The surface of the sea looks calm, gentle, maybe even predictable. But somewhere in the back of your mind, there's an awareness that beneath that calm is a depth we barely understand. That strange attraction doesn't disappear even when we learn how inhospitable the deepest places truly are. If anything, the more we learn about them, the stronger that pull becomes. There's a certain tension in knowing something exists that we can't fully reach, a place that doesn't bend to our plans or our expectations. On land, we've climbed the tallest mountains, crossed frozen continents, and mapped forests that once seemed infinite. But the deep ocean remains one of the only places left where nature still decides the terms. The idea of something on Earth that remains untouched by us isn't just unusual, it's almost unsettling in a world where everything feels catalogued, photographed, and summarised. The Challenger. Deep stands out precisely because it doesn't fit into the familiar framework of places we can explore freely. And that alone seems to invite a steady, quiet fascination. When people imagine distant worlds, they often picture planets with unfamiliar landscapes or environments that test the limits of our understanding. But for most of human history, the ocean served that role. It was the unknown frontier, even when it was only a short distance from home. The deep ocean, with its pressure, darkness and cold, became a stand-in for the kind of distant realm where normal rules fall away. And because it sits right here on our own planet, that sense of mystery carries a certain weight. We know it's real because we can sail above it. We can measure its depth. We can send machines into it, even if only briefly. We know it's not made of imagination or myth. It's a physical place, silent and steady, waiting beneath us whether we visit it or not. Some people describe the draw of the deep as something instinctual, a leftover thread from a time when humans and the natural world were more closely intertwined. Others see it as the same motivation that pushes us to explore space, or to investigate the smallest particles of matter. It's the desire to understand, to step beyond the comfortable boundary of what we already know. You don't have to be a scientist to feel that pull. Even a simple walk along the beach at night can bring it out. The waves feel endless, the horizon disappears, and the sound of water along the shore creates a rhythm that seems older than anything else around you. There's something about being near the ocean that encourages the mind to drift beyond the usual limits, almost as if thinking about its depths is a way of stepping outside the routine of everyday life. This attraction isn't limited to the surface. When we think about the Challenger Deep itself, that draw intensifies. Part of it comes from scale. The depth is difficult to visualize, nearly 11 kilometres. If you were to stack the tallest mountain on Earth inside the trench, its peak would still be far below the surface. It's the kind of measurement that doesn't translate easily into human experience. We can climb a mountain, we can walk across a valley, but descending into a place deeper than anything on land is something we can't participate in directly. And when something sits outside our personal scale, it becomes a kind of intellectual and emotional puzzle. We imagine what it must be like down there, even though our imagination has little to anchor itself to. The deep ocean doesn't offer landscapes or colours or sounds that we can picture clearly. It offers pressure, silence and darkness, conditions that don't align with the senses we depend on. That mismatch is part of why the deep holds our attention. Our senses want something to grasp. They want to interpret the world based on touch, sight, sound and movement. When a place removes those familiar cues, it creates a kind of quiet void that draws us in instead of pushing us away. It's the same feeling that comes from looking at a night sky full of stars. You don't see the details. You see hints, outlines, possibilities, and in that uncertainty you find space to wonder. The Challenger Deep offers that kind of space. You can't picture it clearly, but you know it's there, and knowing it's real adds weight to the unknown. Another part of the pull comes from the life that exists in these depths. Even though we've only glimpsed a fraction of it through brief expeditions and remote cameras, what little we've seen doesn't match our expectations. Organisms that live under enormous pressure should, by all rights, look fragile or distorted. Instead, they have adaptations that make survival possible in conditions that seem impossible for anything else. Soft-bodied creatures drift slowly through the darkness. Tiny organisms produce their own faint light. Strange, delicate animals wait in the cold, as if time moves differently for them. These glimpses remind us that life doesn't follow the rules we assume it does. It finds a way to exist in places we consider uninhabitable. And every time we discover something alive at those depths, the urge to know more grows stronger. There's also something humbling in knowing that life has been thriving in the deep long before we even knew such depths existed. The ocean's surface is familiar, but beneath it lies a world shaped by pressures and temperatures that don't match anything we associate with habitability. The fact that anything can survive there adds another layer to our fascination. It shows us that the limits we understand are not universal. They're shaped by our perspective, our bodies, our experiences. The deep doesn't care about those limits. It supports life on its own terms, in its own way. And that quietly challenges the idea that humans fully understand the natural world. Some people are drawn to the Challenger Deep because it offers the kind of mystery that doesn't need dramatic effects or elaborate explanations. The environment speaks for itself. It doesn't change quickly. It doesn't send signals of activity. It simply exists in a steady state that hasn't been shaped by human presence. There's a certain reassurance in that. In a world where so much changes rapidly, where human influence reaches into almost every ecosystem, the deep ocean remains largely untouched. Not because we lack interest, but because the conditions make our presence nearly impossible. When something remains beyond our reach, it becomes a point of quiet focus. There's also the historical pull. For centuries, people speculated about what might be hidden below the ocean's surface. Myths and legends grew out of the unknown, imagining creatures and landscapes that fill the gaps in knowledge. Even after we understood that the ocean floor wasn't populated by monsters, the sense of wonder didn't disappear. Instead, it shifted. We started to imagine what real environments might look like, not because of fear, but because of curiosity. The Challenger Deep became part of that narrative. Not a world of danger, but a world of extreme conditions, a place defined not by fantasy but by physics. And exploring physics can be just as compelling as exploring a mythical creature if the environment itself pushes against our expectations. As technology advanced, the pull grew stronger. Submarines, sonar mapping, deep-sea cameras, each new tool let us see a little more, but never enough to satisfy the desire to understand the full picture. It's like peering through a keyhole into a room where the walls stretch far beyond what that narrow view can show. You can see hints of movement, hints of shapes, hints of structure, but not enough to describe the space with confidence. Each expedition into the deep gives us a slightly larger keyhole, but not a door. That limitation doesn't frustrate the curiosity, it strengthens it. People don't lose interest when they learn how little they can see. They lean in closer. Even the physical act of descent plays a role in the fascination. The trip to the bottom takes hours, a slow, steady fall through water that grows heavier and darker with each passing minute. There's no moment when the change becomes dramatic. Instead, everything shifts gradually. Pressure builds, temperature drops, light fades. The walls of a submersible creak softly. Instruments respond more slowly. Communication delays increase. Every meter downward emphasizes how far from the surface you're traveling. Even without witnessing the environment firsthand, the experience itself reinforces the sense of entering a world that doesn't share anything with our familiar one. And that experience, whether lived or imagined, contributes to the pull. Many people describe the Challenger Deep as a frontier, but it's unlike any frontier humans have approached before. Other frontiers allowed us to walk, climb, build shelters, gather food, or establish a presence. This one doesn't. You can't breathe the air. You can't walk on the floor. You can't stay there for extended periods. You can't create structures that would allow long-term exploration. This isn't because the environment is unfriendly in an emotional sense. It simply operates under rules that don't match our biology or our tools. When faced with an environment that doesn't bend, humans often find themselves wanting to understand it even more. The Challenger Deep has that effect. It doesn't push back aggressively. It doesn't threaten. It just remains inaccessible, and that inaccessibility isn't something we can remove through determination alone. It isn't a matter of training harder or practicing longer, or committing more resources. It's a matter of physics and engineering reaching their limits. When a place sits behind physical limits rather than logistical ones, the human mind starts to treat it differently. It becomes a point of long-term interest rather than an obstacle to conquer. People think about what lies there not because they expect to enter it easily, but because they know it will always remain difficult. Difficulty combined with possibility is a powerful combination. It keeps interest alive even when access is limited. There's also the simple truth that the deep ocean represents something separate from human history. It hasn't been shaped by us. It hasn't been altered by buildings, traffic, pollution, agriculture, or any of the pressures that define environments on land. Even places we consider remote, mountain ranges, deserts, forests, carry traces of human presence. But the Challenger Deep holds no such marks. It continues unaffected, unchanged, and largely unseen. That makes it one of the few places left where the natural world operates in a state that predates us entirely. There's a calmness in that thought, a reassurance that the planet contains layers of existence that don't rely on or respond to human activity. And that calmness continues to draw us outward. People feel a connection not just to the mysteries we discover, but to the idea that something can remain outside our reach. There's room in that kind of distance. Room for thought, room for imagination, room for a sense of scale that's hard to find elsewhere. It's not about conquering or claiming, but about acknowledging that the world is larger and more complex than the parts we interact with daily. The Challenger Deep isn't a puzzle we're trying to solve as quickly as possible. It's a reminder that some questions take time, patience, and a willingness to accept partial answers. The fascination grows each time we learn something new, not because the new information solves anything, but because it expands the horizon of what we still don't know. A sediment sample reveals unexpected chemical compositions. A camera captures a creature that doesn't resemble anything found near the surface. A pressure-resistant sensor records a sound no one can identify. Each new piece adds to the story, But the story never becomes smaller or simpler. If anything, it becomes broader. And that broadness sustains the pull. As we keep drifting downward in our quiet journey, that pull becomes clearer, not because we've resolved it, but because we've leaned into it. The deep holds our attention, not through spectacle, but through steadiness. Through the quiet knowledge that it exists far beyond what we can comfortably enter, yet invites thought and curiosity all the same. And with each passing moment, there's more to explore in how this pull shapes our approach to the world beneath the waves, setting the stage for everything else that waits ahead. When we keep travelling downward through the ocean, the first things to fade are the ones we normally rely on without thinking. Light, warmth, movement, colour, sound in the way we usually interpret it. Everything familiar starts slipping away long before we get anywhere near the deepest trenches. It doesn't happen abruptly. There's no single moment where the world shifts into something foreign. Instead, the surroundings change little by little, quietly, as if the ocean prefers to introduce its extremes with patience rather than drama. It's this slow transition that sets the tone for the environment waiting far below. A place shaped not by our expectations but by physics working with steady persistence. Most people imagine the deep ocean as pitch black, but that total darkness doesn't begin immediately. The upper layer, where sunlight still reaches, feels somewhat recognisable. Colours appear normal. Fish dart through sunlit water. Plants grow in places where light can support them. Even a casual swimmer or diver can enter this zone without difficulty. But the deeper we go, the more the sunlight thins and weakens until it scatters into faint, washed-out beams. The ocean absorbs red light first, leaving everything tinted in shades of blue and green. Then the greens fade, then the blues. Eventually only the faintest remnants of dim, filtered light remain. And then, nothing. At a certain point, even the brightest sunshine from the surface can no longer penetrate the layers of water above. Darkness becomes complete. This isn't the kind of darkness we experience at night on land. It isn't influenced by moonlight, city lights, starlight, or reflections bouncing off clouds. It's a darkness with no sources, no interruptions. A darkness that doesn't shift or lighten or react. It surrounds everything evenly from all directions. Even high-powered lights from submersibles only illuminate a very small cone in front of them, and that light gets swallowed quickly by the water, disappearing almost as soon as it appears. This kind of darkness defines the environment in the deep, not as a dramatic effect, but as a steady fact of existence. Life down here doesn't rely on sight the way surface creatures do. It adapts in other ways, using senses that work independently of light altogether. As the light fades, the temperature changes too. At the surface, warmth from the sun heats the upper layers, making the water comfortable to swim in during certain seasons. But warmth doesn't travel far downward. Within a short distance, the temperature drops noticeably, becoming cooler in a slow, steady descent. Eventually, the water reaches a stable low point just above freezing. It doesn't get colder after that, not because the deep sea is warm, but because the temperature reaches a kind of equilibrium at those depths. There's no seasonal variation, no fluctuation from day to night. The cold is constant. Machines must be able to operate at that temperature indefinitely, and any biological organism must be adapted to function in an environment where heat is practically non-existent. What might be surprising is that this cold doesn't feel sharp or biting, the way cold air does on land. Water conducts temperature very efficiently, so the chill here is uniform. It wraps around everything evenly. But because we aren't physically present in our own bodies, we experience it through measurements and instruments rather than sensation. The cold doesn't fluctuate, doesn't ease, and doesn't respond to currents in the way we're used to. It's simply the baseline condition of the deep, a steady, unchanging low temperature that defines everything that lives or operates there. Pressure also grows steadily as we sink. There's no warning before it begins, no physical sign. But the deeper we descend, the more it builds. The water above us accumulates into a weight that presses inward from all directions. On the surface, pressure is something we take for granted because it acts on us in ways that feel normal. But in the deep, the pressure becomes a dominant force. Every 10 meters of depth adds the equivalent of another atmosphere. After a few hundred meters, the pressure is strong enough to crush unprotected objects. After a few thousand meters, the force is beyond anything humans can safely encounter without reinforced equipment. By the time we approach the kinds of depth associated with the Challenger Deep, the pressure becomes almost impossible to conceptualize. It's more than 1,000 times what we experience at sea level. That means every square inch of a submersible hull is enduring an amount of force that would easily destroy everyday materials. Titanium begins to flex. Steel becomes vulnerable. Even specialized synthetics and composites must be designed with extreme precision to survive. Anything containing air must be reinforced from every direction. Anything built with moving parts must be engineered to function in an environment where every joint, seal and valve is under extraordinary stress. The conditions here don't resemble anything we experience in everyday life. There's no equivalent on land. Even the crushing pressure inside industrial systems or deep mines doesn't approach what exists near the ocean floor. The deep ocean doesn't need to announce its hostility. It simply applies force, continuously, uniformly, everywhere. And because that pressure is invisible, we rely entirely on instruments and engineering to grasp the reality of it. Sound behaves differently down here too. Water transmits sound efficiently, meaning sounds can travel long distances, but the environment is so still that sound doesn't behave the way we expect it to. There's no echo in the way we experience echoes in open spaces above ground. Instead, sound can feel muted or distorted. Some frequencies travel easily, others are absorbed. Communication between machines becomes slower, less reliable. Signals take longer to reach the surface. When remotely operated vehicles move through these depths, they rely on sound-based systems that must navigate through this unusual acoustics. Operators on the surface must account for delays, distortions, and the unique challenges of sending commands through layers of dense, cold water. The environment also removes familiar landmarks. There are no trees, no rocks in the sense we recognize them, no visual markers that help us orient ourselves in space. The seafloor can be flat, sloping, or scattered with sediment, but it doesn't resemble any landscape we walk on. The terrain formed by tectonic forces doesn't present itself clearly through the darkness either. Machines can use sonar to map surfaces and obstacles, but the human mind struggles to picture these places because our spatial understanding depends heavily on visual cues. Without those cues, the deep becomes a place that exists only through indirect data. Lines on a sonar map, recorded footage in narrow beams of artificial light, pressure readings, temperature records, and chemical measurements. Life in these depths, though present, doesn't provide a sense of familiarity either. The creatures that live here don't resemble the animals we see near the surface. Many have soft bodies to withstand pressure. Others have slow metabolisms to conserve energy in an environment where food is scarce. Some produce their own light through chemical reactions, but none of them anchor the environment in a way that gives us comfort or recognition. We look at them with interest, but there's no sense of connection in their features or behaviours. They aren't dangerous. They aren't comforting. They simply fit the deep in ways we cannot. Even the movement of water changes at these depths. Currents exist, but they're slow and steady rather than turbulent. The environment doesn't pulse with waves or tides in the way the surface does. It feels almost motionless, not because nothing is happening, but because everything happens at a pace that is difficult for humans to relate to. Sediment drifts slowly. Organisms move with deliberate pacing. Chemical reactions occur gradually. When we picture active ecosystems, we think of constant interaction, fast movement, visible change. The deep offers none of that. Its stillness isn't peaceful or ominous. It's simply the result of an environment shaped by limited energy, vast pressure, and restricted resources. Because the deep ocean differs so completely from our familiar world, even the simplest tasks become complicated. Maneuvering a submersible requires careful planning because visibility is limited and response times are slow. Turning around in tight spaces requires navigation systems that can operate with precision despite the darkness. Collecting samples demands specialized tools that must work under crushing pressure. Even taking photographs becomes a challenge because artificial lighting must be strong enough to illuminate while still being efficient and reliable at low temperatures. Every action becomes something that must be adapted to the environment rather than imposed upon it. That is perhaps the most defining feature of this region. Above ground, we design tools to shape the environment around us. Down here, the environment shapes everything we bring into it. There's no option to modify conditions, remove obstacles, or create controlled settings. Every device must perform under the conditions given, and those conditions are unforgiving. Even the idea of staying for extended periods isn't feasible. Human-piloted submersibles are built with thick, reinforced hulls designed to survive enormous pressure, but they can only carry limited supplies. Battery systems limit travel time. Life support systems restrict how long people can remain inside. Heat generated by equipment must be managed in an environment where the surrounding water is extremely cold. Every constraint limits the time available for observation and research. Even robotic systems face similar restrictions. Some are tethered to the surface. Others rely on battery systems that must last long enough to make the journey and return with data. The deep doesn't offer opportunities for long-term exploration without constant, extensive support. The farther we descend, the more these limitations become apparent. The environment isn't unwelcoming in an emotional sense. It's simply structured in ways that don't align with human needs or expectations. It doesn't adjust to accommodate us. It doesn't resist with intention. It exists according to physical laws working with steady consistency. Light disappears, temperature drops, pressure builds, sound travels differently, movement slows, familiar forms fall away. Everything that makes the upper world recognizable gradually fades until what remains is a zone shaped entirely by conditions that differ from anything we live within. This place beyond light, warmth, and familiarity isn't hostile by design. It's simply the result of depth and physics interacting in ways that our bodies and tools aren't built to inhabit freely. Our fascination lingers because these conditions create an environment that we can study only from behind layers of protective technology. And as we continue drifting downward in this journey, those same conditions become the foundation for understanding why reaching the deepest point on Earth remains such a challenge, setting the stage for everything that follows in the layers below. The deeper we continue travelling, the more one factor begins to dominate every part of the descent. It isn't the darkness, even though the absence of light changes the environment more completely than anything we know on land. It isn't the cold, even though the temperature settles at a level that would make most materials brittle and most forms of life slow almost to stillness. It's the pressure. Not the kind you feel at the bottom of a swimming pool or during a deep breath, but a force that increases steadily until it reaches a scale that feels unreal when you try to think about it in human terms. Pressure becomes the defining quality of these depths, not because it grabs attention dramatically, but because it operates non-stop in every direction, affecting every object and every structure with equal relentless weight. At the surface, the atmosphere above us exerts pressure on everything, but we don't notice it because our bodies are adapted to live within it. In water, pressure increases far more quickly. Every 10 meters of depth adds the equivalent of another full atmosphere. It doesn't take long for that number to climb. At 100 meters, the pressure is already 10 times that of the surface. At 1,000 meters, it becomes 100 times greater. And as we continue sinking, that increase doesn't slow down or taper off. It grows with each meter, building in a way that feels almost impossible when you consider the cumulative total at the deepest known point on Earth. The Challenger. Deep sits beneath nearly 11 kilometers of ocean. The pressure there is over 1,000 times what we experience at sea level. Each square inch of a submersible hull must handle the kind of force that would easily crush ordinary metals, glass, plastics, or anything containing air. The pressure doesn't strike suddenly. It doesn't pulse. It simply applies a constant inward push that surrounds everything evenly. This uniform force is what makes survival at these depths so difficult. There's no escaping it, no moving into a pocket of lower pressure, no adjusting position to lessen its effects. It is everywhere at once. When engineers design machines for these depths, they can't rely on a single trick or material. Every part must be planned with precision. Any component that contains air becomes a potential failure point. Any weak spot, even one too small to see with the eye, becomes a risk. Pressure at these depths doesn't negotiate. It finds that weakness and pushes until the material gives way. If a hull collapses, it does so instantly. There's no gradual deformation, no warning, no time to react. That kind of failure happens faster than human reaction time, and with an energy release that leaves nothing recoverable. This is why deep-sea machines are built with spherical pressure hulls whenever possible. A sphere distributes pressure evenly, preventing weak points from forming in corners or flat surfaces. Early attempts at creating vessels to withstand deep ocean pressure were limited by the materials available. Iron and steel provided strength, but even thick layers of metal began to bend or crack under extreme forces. Engineers experimented with layered materials, shape modifications, reinforcement rings, and new alloys. Each improvement offered a step deeper, but the pressure increased so fast that even a small gain in depth required significant engineering advances. It wasn't enough to simply make the walls thicker. Weight became a problem. A hull thick enough to withstand extreme depths would become so heavy that keeping it buoyant would require enormous amounts of flotation material. But flotation materials must also withstand pressure. Anything containing air would collapse. This led to the use of syntactic foam, a material made of microscopic hollow spheres embedded in resin. The spheres themselves are made from glass or ceramic and are engineered to resist collapse under extreme pressure. The foam provides buoyancy without the risk of compression at depth. But even syntactic foam has limits. At certain pressures, it begins to deform. Its buoyancy decreases. Engineers must calculate exactly how much can be used without risking failure. Every calculation must be conservative. The deep doesn't forgive errors. Pressure affects electronics as well. Circuits, solder points, connectors, lights, and motors behave differently when the surrounding environment applies thousands of pounds of force to every surface. Some systems must be sealed inside pressure-resistant housings. Others must be filled with oil so that there are no air pockets for pressure to collapse. Oil-filled housings equalize internal and external pressure, but they require flexible walls that allow slight deformation without breaking. Designing electronics that can function reliably inside these housings becomes another layer of complexity. Heat generated by the system must disperse into cold water without causing condensation or temperature shocks inside the components. Even simple movements become difficult in environments with high pressure. Motors require more torque to move robotic arms or thrusters. Lubricants behave differently. Bearings and seals face increased friction under compression. Materials that work well at the surface may seize or deform at depth. Every moving part must be designed to tolerate pressure that acts like a constant vice. Engineers test these parts in specialized pressure chambers on land, but these tests can only approximate the complex conditions found in the real environment. High pressure also affects chemical and physical properties of materials in ways that don't always appear in surface-level testing. Some metals become stronger under compression, while others become brittle. Plastics deform, adhesives fail, gaskets lose flexibility, paints and coatings crack. The stresses don't occur in sudden jumps, they accumulate slowly throughout the descent. A device that functions perfectly at 6,000 meters may fail without warning at 7,000, even if the structural change is small. By the time the machine reaches 10,000 meters, any error in material choice or assembly becomes a serious risk. This is why so few vehicles have reached the Challenger Deep successfully. The ones that have were built with extreme attention to detail, using materials selected specifically for their behaviour under pressure. The sphere that houses the pilot must be machined from solid metal blocks with no welds or seams. Any tiny inclusion of air within the metal becomes a weakness that could cause the material to fracture. Even machining marks left inside the sphere must be polished out because small surface imperfections can lead to stress concentrations. The tolerances involved are incredibly tight. One of the earliest successful deep-sea vehicles was the bathyscaphe Trieste, which reached the bottom of the Challenger Deep in 1960. Its cruise sphere was made from steel, and it carried gasoline for buoyancy because gasoline compresses less than air. The thick steel sphere kept the pilot safe, but the rest of the vessel groaned and creaked under pressure. Windows, viewports, and even bolts had to be designed with immense care. The Trieste survived the journey, but it wasn't built for repeated trips. Every descent stressed the materials. Modern deep-sea vessels use titanium, a material that performs better under pressure and resists corrosion. Titanium spheres are incredibly strong, but they're also difficult to manufacture. Welding titanium risks creating brittle areas. Machining large titanium spheres requires specialized tools and techniques, and even with titanium, the thickness of the hull must be calculated precisely. Too thin, and it risks collapse. Too thick, and the vessel becomes too heavy for available buoyancy materials to lift. Remote-operated vehicles face similar issues. Their frames must be strong enough to resist pressure but light enough to remain maneuverable. Their cameras and sensors must be sealed or oil-filled. Their cables must withstand pressure and mechanical stress over long distances, and their thrusters must be powerful enough to overcome drag in dense water, but efficient enough to operate on limited power. Pressure also complicates emergency procedures. If something goes wrong at the surface, people can intervene. If something goes wrong at 1,000 meters, recovery becomes difficult but not impossible. But at 10,000 meters, intervention is not realistic. A malfunction becomes a permanent loss. This forces engineers to design systems that can resolve problems autonomously or avoid them entirely through redundancy. Multiple backup systems are required, but each backup adds weight and complexity. The balance between safety and feasibility becomes delicate. Pressure affects even the sediments and rocks found at the bottom. They compact over time under the weight of the water above. Machines landing on the seafloor must do so carefully because the ground can behave unpredictably. It may appear solid, but under pressure, the fine sediments behave almost like a dense fluid. If a vehicle sinks into the sediment, extricating it becomes extremely difficult. Thrusters can stir up clouds of fine material that obscure visibility for long periods. Even stable landing legs must be designed to distribute weight carefully to avoid sinking. As pressure shapes the environment, it also limits the types of experiments researchers can conduct. Instruments designed for shallow water can't survive. Chemical sensors may crack. Biological sampling devices might fail if pressure forces water into places they weren't designed to handle. Even simple containers must be reinforced. If they hold samples from the deep, bringing them to the surface changes the pressure around them so quickly that biological specimens may die, or physical samples may change structure. This makes studying deep-sea organisms or chemical conditions difficult, because the act of retrieval alters the environment the samples came from. The deep challenges not only our materials but our imagination of what machines can endure. When we think about engineering limits, we often imagine stretching existing materials slightly, modifying shapes, or adding reinforcements. But in the deep, the difference between survivable pressure and catastrophic collapse may be just a few hundred meters. It creates a boundary that technology cannot cross without major leaps in science and engineering. Even with all the advancements we've made, every descent into the Challenger Deep carries uncertainty. Machines return with dents, scratches and warping that show the force they endured. Sometimes sensors malfunction, sometimes lights flicker, Sometimes data is corrupted because electronics were pushed to their limits. The environment doesn't damage machines dramatically. Instead, it applies steady pressure that tests every part simultaneously. And even when a descent is successful, the experience emphasizes how far we are from creating machines that can operate freely and reliably in this environment for long periods. Nothing at these depths is routine. Every expedition requires planning, resources, and careful thought. The deep remains a place where pressure continuously asserts itself, reminding us that survival here depends entirely on respecting the limitations of materials and design. As we continue moving downward through this journey, pressure becomes not just a physical challenge, but a constant reminder of why the deepest point on Earth remains out of reach for long-term exploration. The machines we send into this environment must be built with precision and care, yet even the strongest designs encounter limits imposed not by imagination, but by the unchanging physical reality of the deep ocean. And every metre deeper reinforces how far this place stands from the conditions we consider normal, guiding us further into the difficulties that shape everything waiting below. As we continue drifting downward, the darkness that surrounds the deep stops feeling like an absence of light and starts becoming something with its own presence, something that shapes the entire environment. It isn't dramatic, and it doesn't arrive all at once. It builds gradually with every passing metre until the last traces of surface brightness dissolve completely. The change happens quietly, and because the descent takes so long, you start to notice the subtle ways light interacts with water before it disappears altogether. What begins as dim shapes slowly becomes patches of shadow, then outlines that feel hesitant, and eventually a condition where nothing visible remains beyond what artificial lighting can reach. Sunlight weakens in layers. First the reds fade, absorbed quickly by the water. Then the oranges and yellows disappear. Then the greens. Even the deep blues, which travel farther, begin to shrink until they vanish entirely. The last natural photons we see at depth are faint and scattered, arriving at angles that make them feel out of place, like visitors from a world that no longer applies here. Once those final traces are gone, the surrounding environment settles into a darkness that is complete, uninterrupted, and not influenced by the movements of the surface above. Most people imagine darkness as something passive, something empty, but in the deep oceans, the absence of light changes everything so thoroughly that it begins to define the space in ways we don't normally think about. Our eyes are built to interpret reflections, contrasts, shadows, and shapes. They rely on light bouncing off surfaces. Without that, they provide almost no useful information. The brain, accustomed to patterns formed by illumination, has nothing to interpret. The result isn't simply visual blindness, it's a shift in how the environment can be perceived at all. In total darkness, familiar senses lose their usual priority. Vision, which humans rely on heavily, becomes almost meaningless. Hearing offers limited help because sound travels efficiently in water but doesn't create clear directional cues the way it does in air. Touch isn't useful beyond the boundaries of the submersible. Smell and taste provide no information at all. That leaves us with instruments: sonar, depth sensors, pressure gauges, cameras with artificial lights, none of which reflect what the human body evolved to navigate. Down here, the darkness reshapes the limits of what can be known through direct experience. It becomes a kind of environmental structure, not because it has form, but because it sets boundaries on what interacting with this world can look like. Machines that operate in this environment rely on artificial lighting, but even those lights behave differently than we expect. A powerful spotlight that can illuminate a large room on land only reaches a short distance here. Water absorbs and scatters the light, causing it to fade quickly. The beam forms a narrow cone, bright in the immediate area, and then swallowed completely beyond a few meters. This creates a kind of tunnel vision, a confined zone of visibility surrounded by uninterrupted blackness that doesn't care how bright the lamp is. If you've ever walked through fog with a flashlight, you might expect a familiar effect, but the ocean isn't fog. Fog still allows some diffusion, some dim outline. The deep allows none. When the light ends, it ends sharply, leaving not a hint of what lies beyond. Even if something sits only a few meters outside the illuminated area, it remains invisible. The darkness forms a boundary around every object, every movement, every measurement. It's not something that can be pushed back indefinitely. No matter how much power is put into the lamps, the water eventually absorbs the output. This limitation affects everything we do down here. Cameras can't capture wide scenes. Maps must be built slowly through sonar, one pass at a time. Vehicles must navigate carefully because they can't see obstacles until they are very close. Even reading instruments inside the submersible takes on a new significance, because those instruments become the only reliable indicators of what surrounds the vessel. Darkness so complete requires constant interpretation through data, rather than direct perception. It also changes the way time feels. Without visual cues, the hours pass in a way that feels disconnected from the familiar rhythm of sunrise, sunset, or shifting shadows. In this environment, there is no distinction between morning and night, no changes in brightness that signal movement through the day. For a human inside a deep-sea vehicle, the interior lighting becomes the only stable point of reference. This creates a sense of isolation not driven by emotion, but by the absence of environmental cues that normally anchor us in place and time. Even the concept of distance becomes difficult. On land, the brain uses visual markers to estimate how far away objects are. In the deep, those markers don't exist. The boundaries of the environment do not provide perspective. When the only visible space is the narrow area illuminated by artificial light, everything beyond that beam feels unreachable. It isn't just darkness. It's the removal of spatial reference, which affects movement, orientation, and understanding of scale. This is especially important when considering how submersibles interact with the terrain. The seafloor in the Challenger Deep isn't flat. It contains slopes, trenches, variations in sediment thickness, and scattered biological or mineral features. But because the darkness hides these features completely until the vehicle is directly above them, navigation must proceed cautiously. Even advanced sonar can only map at certain resolutions. The darkness makes ordinary piloting techniques ineffective. Operators rely on instruments to build a mental model of the surroundings, because visual confirmation isn't available. Some might imagine the deep-sea darkness as eerie or unsettling, but the reality is more practical than emotional. The sensation isn't fear. It's simply the recognition that familiar cues are gone. That recognition becomes part of the environment itself. In a sense, the darkness functions as a natural limit. It restricts what can be perceived without damaging equipment or venturing too close to terrain that hasn't been mapped. It dictates movement speed, exploration boundaries, and sampling methods. Life down here has adapted to the darkness in ways we can't replicate. Organisms either produce their own light through bioluminescence or operate without any reliance on vision. Some animals use chemical signals, others detect vibrations, some drift opportunistically, moving slowly through the water in search of nutrients. Their survival strategies don't require them to see the environment. They navigate through an entirely different set of cues that humans can't use. The adaptations of these species make it clear that darkness is not a temporary inconvenience for them. It is the constant environmental condition under which evolution shaped them. Bioluminescence might seem like a solution to the darkness, but the light it produces is low in intensity and specific in purpose. It can be used to attract prey, communicate, distract predators, or camouflage movement. But it does not illuminate the environment in the way we might expect. A small flash might create a subtle glow, but it doesn't reveal the surrounding space. Each organism uses light strategically, almost sparingly, because producing it requires energy. And in a place where food is scarce, energy cannot be wasted. Machines, however, cannot mimic these organic strategies. They rely on external power, structured systems, and specific engineering principles that were not designed with total darkness in mind. Artificial lights provide temporary visibility, but they come with limitations. They consume power, they attract organisms, they can reflect off particles and create glare. They reveal only narrow slices of the environment, and because the darkness outside them remains constant, turning off the lights plunges everything back into an absolute blackness that doesn't wait or adjust. It simply dominates again. One unexpected effect of this darkness is the way it influences our understanding of the seafloor. When explorers describe the bottom of trenches like the Challenger Deep, they often mention how limited the visible area is. Even after reaching the seafloor, the darkness makes the immediate surroundings feel small, almost confined, despite being in one of the largest, deepest geological formations on Earth. The scale of the environment isn't visually accessible. Only sensors and long-term mapping efforts can reveal how wide and complex the terrain truly is. This is one reason the deep feels like its own landscape. Not because it has visible features shaping the space, but because the darkness itself dictates how the space can be perceived. In a sense, the darkness becomes the main interaction point. Everything else must be discovered through effort, tools, and patience. The lack of light doesn't simply hide the environment. It forms the backdrop against which every exploration attempt must operate. Darkness of this kind also impacts how sound appears. In shallow waters, sound bounces off surfaces, creating echoes that help with orientation. But in deeper regions, those reflections become faint or distorted. Without visual cues, sound alone becomes difficult to interpret accurately, especially when the environment contains uneven terrain or suspended sediments. Acoustic instruments must compensate for these challenges, and even then they sometimes produce ambiguous readings that require careful analysis. Because darkness removes so many familiar cues, it changes how data is collected. Scientists can't rely on visual surveys. Instead, they map the terrain using sonar and combine multiple passes to form a larger picture. Sample collection relies on mechanical arms guided through narrow viewing windows. Every action involves translating instrument readings into decisions, rather than simply observing a scene. This constant translation becomes part of the exploration process, influenced not by fear of the unknown, but by the inherent limitations created by the darkness. Even for machines designed specifically for deep-sea operation, the absence of light complicates routine tasks. Cameras require continuous artificial illumination, which consumes energy that could otherwise be used for maneuvering or data collection. Lights can overheat if not properly cooled by surrounding water. If sediment is disturbed, it reflects the light back into the lens, creating haze that obscures visibility. Each of these challenges stems from the basic fact that natural light cannot support visibility here. Darkness becomes a defining environmental factor, not because it is dramatic, but because it quietly removes the sensory framework we rely on. It doesn't change or respond. It simply remains constant at every depth beyond the reach of sunlight. And because it is constant, it forces exploration to adapt around it, using indirect methods instead of direct observation. As we keep descending on this slow, steady journey, the darkness continues to shape how the environment must be navigated and understood. It doesn't fade or soften. It remains as complete at 10,000 meters as it is at 4,000, and because of that, it becomes one of the central reasons why exploring the deepest regions of the ocean remains a challenge built not on dramatic danger, but on the steady, unchanging fact that without light, the world becomes something the human mind must interpret through tools rather than through direct experience. As we continue moving deeper into the ocean, the environment begins to show signs of life that don't align with the familiar images many people carry when they think about the natural world. These creatures aren't here to impress or alarm. They simply exist in conditions shaped by pressure, darkness, and scarcity. Yet their presence quietly challenges assumptions about what life needs, how it behaves, and where it can survive. Seeing these organisms for the first time, whether through footage or sensors or direct observation from a submersible window, often brings the realization that the deep is not empty. It's a functioning ecosystem, with species adapted to pressures and temperatures that would quickly destroy anything built around the requirements of surface life. Most people imagine deep-sea animals as unusual shapes floating in darkness, and some of them do match that expectation. But even those creatures operate with logic. Their features aren't strange for the sake of being strange. They are solutions, built through slow adaptation to problems created by the environment. When light disappears completely, having large eyes becomes pointless unless those eyes can detect the faintest glimmers of bioluminescence. When pressure reaches levels that would crush a terrestrial organism, bones weaken, soften, or disappear entirely to avoid structural failure. When food becomes scarce, animals slow their metabolisms, drift more often, or develop strategies to take advantage of small food particles falling from above. As the depth increases and the environment becomes less familiar, life becomes specialized rather than chaotic. Every adaptation reflects the physics of the deep. For example, many fish found at several thousand meters have bodies without air-filled swim bladders. Air compresses under pressure, so a bladder would collapse and destabilize the animal. Instead, these species use oils, fats, or gelatinous tissues to maintain buoyancy. These materials don't compress the way air does, allowing the fish to remain neutrally buoyant without fighting constant pressure changes. Some deep-sea creatures have transparent bodies, not for camouflage in light, but because pigmentation is unnecessary in darkness. Others have shapes that appear flexible or soft, because rigidity becomes a liability when pressure is constant. If the body can deform slightly without breaking, it survives. Many organisms rely on slow movement because conserving energy is essential in a place where food is limited. The idea of an animal hunting constantly or darting quickly through the water doesn't fit the reality of this environment. Motion comes with a cost, and slow, steady drifting becomes a more efficient strategy. Bioluminescence, often imagined as a dramatic glow, plays a practical role. For some animals, it attracts prey. For others, it distracts predators. Certain species use it to communicate. Some use it to blend with faint downwelling light far above, creating a form of counter-illumination that hides their silhouette. The glow itself is usually blue or green, because those wavelengths travel farthest in water. It isn't bright enough to illuminate surroundings. It functions instead as a tool with specific behavioral purposes. When a fish flashes a pattern of light, it can be compared to sending a message rather than lighting up a room. One example of adaptation can be found in amphipods, small crustaceans that live at depths reaching into the hadal zone. Amphipods might appear simple, but their ability to survive extreme pressure teaches us something important. Their cell membranes contain special molecules that prevent them from becoming rigid. Their proteins have structures that remain functional in conditions that would destabilize ordinary proteins. They rely on lipids that behave differently under pressure. These details reveal how survival in the deep begins at the molecular level. It isn't just a matter of body shape or external features. It involves biochemical adjustments that allow life to operate under conditions that would ordinarily disrupt cellular processes. Certain fish, like the snailfish found in the Mariana Trench, show this principle even more clearly. Snailfish don't look like creatures built to endure extreme environments. Their bodies are soft, almost delicate, but softness becomes an advantage. Without rigid bones, their bodies avoid fracturing. Without air pockets, they avoid compression. Their cells contain compounds that help stabilize proteins against pressure. Their digestive systems are adapted to handle the low-energy food available at these depths. They eat amphipods and other small organisms that drift along the sea floor. Their existence demonstrates that even vertebrates can adapt to near-impossible conditions with the right combination of traits. Some deep-sea organisms don't rely on sunlight indirectly or directly. They live far below the reach of photosynthesis. Instead, they depend on food that drifts down from above, known as marine snow. Marine snow consists of small particles, organic debris, dead organisms, fecal matter, and bits of material shed from surface ecosystems that drift down slowly over days, weeks, or even months. It's a low-energy resource, but in the deep, every particle counts. Some species have adapted to filter this material. Others search for larger items that fall from above, such as the remains of whales or large fish. These rare events provide bursts of nutrients that can sustain entire communities. Even in total darkness, some environments become hospitable through chemical reactions. Hydrothermal vents, located along mid-ocean ridges, release mineral-rich fluids that support ecosystems driven by chemosynthesis rather than photosynthesis. Although vents don't typically reach the depths of Hadal trenches, they illustrate a principle. Life can exist without sunlight if other energy sources are available. Chemosynthetic bacteria form the base of these vent ecosystems, supporting tube worms, crabs, clams, and other organisms. While these systems don't directly explain life in the Challenger Deep, they reveal that life on Earth can adapt to conditions far outside the familiar range. In the Hadal zone, life is generally sparse compared to the surface, but that scarcity doesn't mean absence. It means that each organism must be efficient. Deep-sea holothurians, or sea cucumbers, sift through sediment to extract nutrients. They move slowly, conserving energy. Their bodies often appear elongated or soft, matching the need to withstand pressure. Some species float above the seafloor and filter organic material. Because they face minimal predation and little disturbance from currents, their adaptations focus more on survival than on rapid response. Certain worms, isopods, and other invertebrates also inhabit these areas. Some have bodies that flatten under pressure to maintain structural integrity. Others rely on thick outer layers that resist deformation. Their internal fluids have chemical balances that differ from surface organisms. These differences prevent cells from collapsing or malfunctioning under pressure. Even microorganisms thrive here. Microbial life persists in sediments where pressures are too high for most complex organisms. Bacteria and archaea in the deep possess enzymes and proteins built to function in these extreme conditions. Some of them rely on chemical gradients within the sediment for energy. Others break down organic matter slowly, contributing to the deep-sea nutrient cycle. These microbes might not be dramatic in appearance, but they demonstrate something essential about life's range. They operate where energy is scarce, movement is minimal, and pressure is constant. They turn small chemical reactions into survival strategies that work where other life forms cannot function. One of the challenges in studying these creatures is bringing them to the surface. When an organism adapted to high pressure is retrieved without protection, the sudden drop in pressure can cause its body to expand, rupture, or collapse. Some species cannot survive the ascent at all. For this reason, scientists use pressure-retaining containers to bring samples up for research. These containers preserve the conditions of the environment, preventing the rapid decompression that would otherwise damage the specimens. But even with these containers, the process is complex. A small mistake can render the sample unusable for study. Footage taken at extreme depths often shows organisms moving in slow, steady ways. Their movements aren't sluggish due to weakness. They're efficient responses to an environment where conserving energy is key to survival. A quick burst of motion would consume more energy than their ecosystem can reliably provide. Slow drifting, slow feeding, slow growth. These traits align with low resource availability and the physical limitations of the deep. Even predators behave differently here. When a fish hunts in the deep, it doesn't chase prey across large distances. It waits. It relies on vibrations, chemical changes, or bioluminescent cues to detect potential food. When it strikes, it must do so precisely because missing an opportunity means waiting much longer for another. This hunting style isn't dramatic. It's built on patience and timing. A large mouth or expandable stomach often helps. If a rare large meal appears, the predator must take advantage of it fully, since it may not see another for a long time. These survival strategies show how life adjusts not just behavior, but structure and biochemistry to fit an environment that seems openly incompatible with biology. Each organism answers a question we didn't know existed. What does life look like under immense pressure, constant darkness, limited food and near-freezing temperatures? The answers vary, but they share common themes: efficiency, flexibility, biochemical stability, and energy conservation. These creatures also bring up questions about the limits of life. When organisms thrive at depths humans and most machines struggle to reach, it forces scientists to rethink biological constraints. If life can persist under such pressure, could it exist in similar environments elsewhere in the universe? Could it survive in subsurface oceans on moons like Europa or Enceladus? Could it adapt to chemical conditions we haven't imagined yet? Deep-sea organisms don't answer these questions directly, but they widen the scope of what seems possible. They remove the assumption that life requires a narrow band of temperatures, pressures, and lighting conditions. In studying these creatures, we also learn about how fragile their environment is. Many deep-sea organisms grow slowly, some reproduce infrequently. Their ecosystems depend on a delicate balance of nutrient flow from above. Any disruption to that flow can have long-term consequences. But because the environment is so remote, it has remained mostly protected from large-scale human activity. The organisms here aren't accustomed to sudden changes because their environment doesn't change quickly. Even seismic activity or shifts in the seafloor occur at frequencies that allow these species to adjust over long time scales. The presence of life in the deep doesn't make the environment more accessible. Instead, it reveals how much we don't understand. Every new creature discovered brings both clarity and more questions. The deep isn't empty. It's just different from anything the surface prepares us for. These organisms don't rewrite the rules of life because they defy biology, but because they expand the definition of what biology can accommodate. They show that life, when given enough time, can adapt to conditions far outside what most species can tolerate. Their existence highlights why exploration of the deepest places remains limited. Our machines struggle to survive an environment that living organisms have adapted to over millions of years. Each creature carries within its structure a solution to a problem that human engineering still grapples with. And while these adaptations don't make the deep more accessible, they offer insight into what survival in these conditions looks like. As we continue descending through this journey, the presence of these organisms reinforces the idea that the deep is not a void, but a functioning part of Earth's life systems. Their adaptations offer a guide, not toward conquering the deep, but toward understanding the physical and biological boundaries that shape it. And with each new observation, the environment ahead continues to reveal how much more there is to explore in the ways life responds to the forces at work far beneath the surface. When we keep descending through this slow journey, it becomes clear that the deep ocean doesn't resist our presence through dramatic storms, sudden threats, or visible hazards. Instead, it imposes steady, unchanging conditions that don't bend or ease, no matter how advanced our technology becomes. The challenges aren't theatrical, they're structural. While people often imagine overcoming technological limits through better engineering, more research funding, or more determined innovation, the truth is that the environment at extreme depths places demands on machines that go far beyond what most technologies are designed to withstand. When we talk about technology trembling at the ocean's edge, we aren't describing fear or uncertainty. We're describing the reality that even our strongest tools must operate at the limits of material science, physics, and engineering. Near the surface, technology functions predictably. Electronics work as intended. Motors behave consistently. Mechanical joints move smoothly. Materials maintain their shape. Communication systems respond instantly. But as soon as machines descend, even into relatively shallow depths, those certainties begin to shift. Pressure increases, light disappears, temperatures drop. Electricity behaves differently in cold, dense water. Metals, plastics, and composites experience forces they weren't designed for in everyday environments. At first, these changes are manageable, but the deeper a machine goes, the more these changes accumulate until they compound into a set of challenges that no single engineering fix can solve on its own. Pressure is the most obvious challenge, but it isn't the only one. Every meter adds force. Every force changes how materials behave. At extreme depths, even the strongest hulls must be carved from solid blocks of metal with no seams or joints. Wherever a joint exists, pressure finds it. Wherever a weld occurs, pressure tests it. Wherever there is air, pressure attempts to collapse it. Even materials with high strength-to-weight ratios begin to distort as the external force becomes overwhelming. It doesn't happen suddenly, and it doesn't look dramatic from the outside, but the strain builds. This steady force pushes engineers to work at a scale of precision that most technologies never encounter. Machines designed for ordinary conditions can tolerate minor manufacturing imperfections. A small flaw might reduce lifespan or efficiency, but it won't trigger immediate failure. In deep ocean engineering, flaws are not tolerable. A microscopic imperfection in a hull could become a starting point for a fracture. A poorly tightened bolt can compromise a pressure-resistant compartment. An overlooked air bubble in a synthetic material can turn it into a collapse point. Technology must be built with the kind of precision used in spacecraft or nuclear reactors, except it must remain functional while also being mobile, energy efficient, and durable. The deeper the machine goes, the heavier its protective structure becomes. A vessel designed for shallow research might use aluminum or thin titanium. A vessel designed for thousands of meters requires much thicker metal. But making the hull thicker adds weight. Adding weight requires more buoyancy. More buoyancy requires the use of syntactic foam or other materials that resist compression. Those materials also add weight. Soon, the balance becomes a cycle. Strength requires mass. Mass requires buoyancy. Buoyancy requires structural reinforcement. Each improvement introduces new engineering demands. Unlike land-based machines, deep-sea systems can't vent heat easily. In normal conditions, motors and electronics release heat into the surrounding air. Water in the deep is near freezing, but it cannot carry away heat at the same rate when systems are sealed inside pressure-resistant housings. Overheating becomes a real risk. Designers must either incorporate cooling systems or rely on passive methods that don't introduce additional failure points. The colder the environment outside, the more carefully the heat from inside must be controlled. Lubricants behave differently under extreme pressure and low temperature. Oils thicken or lose their ability to flow. Seals that work well at the surface may stiffen or shrink in the cold, allowing water to enter. Bearings can seize. Rotating parts can fail to move. Engineers often replace lubricants with pressure-tolerant alternatives or encase motors and joints in oil-filled compartments that equalize pressure. But these solutions add complexity to systems that must already operate with limited room for error. Even simple actions become complicated. A robotic arm designed to collect sediment samples must be able to move precisely while operating under forces that squeeze its housing from all sides. The joints must be strong enough to hold shape, but flexible enough not to snap under pressure. The sensors guiding those movements must remain accurate, even when the surrounding temperature and pressure distort their calibration. Each moving component represents a potential point of failure. Electrical systems face additional challenges. High pressure forces seawater into any gap it can reach. Even a microscopic breach in insulation can cause a short circuit. Connectors must be sealed perfectly. Cables must be pressure resistant. Electrical housings must withstand the same conditions as the rest of the vessel, which means they often require their own pressure resistant containers. But adding containers increases weight. Increasing weight affects buoyancy, and buoyancy once again demands more syntactic foam. Engineering becomes a balancing act rather than a single straightforward solution. Communication is another technological limitation that becomes more serious with depth. Radio waves do not travel well underwater. They get absorbed rapidly. At extreme depths, radio communication is essentially non-existent. Light signals travel only short distances. Acoustic signals, which rely on sound, remain the primary method of transmitting information. But sound travels slowly. That delay, even if small, can be significant when a remotely operated vehicle needs to maneuver in complex terrain. This delay means operators must anticipate the vehicle's movements ahead of time. If the machine receives a command half a second late, that could be enough to cause a collision with the seafloor or with unexpected terrain. Automated systems can help, but automation brings its own complications. The vehicle must interpret its surroundings through sensors, which are also influenced by pressure, temperature, and darkness. Even a minor sensor malfunction can compromise decision-making. Energy is another limitation. Deep-sea missions require significant power to run lights, cameras, thrusters, manipulators, and sensors. But batteries lose efficiency in cold temperatures. Power systems must be insulated without overheating. Some missions use tethered cables to provide power from the surface, but those cables must also withstand pressure, abrasion, and movement through currents. They must be long enough to reach the seafloor while remaining strong enough to avoid snapping under tension. Any damage to the cable ends the mission immediately. Navigation becomes more challenging the deeper a vehicle goes. GPS signals do not penetrate water, so positioning systems rely on acoustic beacons, inertial navigation, or surface-based tracking. These systems accumulate small errors over time. In shallower water, errors can be corrected easily. At depth, the darkness and scarcity of landmarks make corrections difficult. The ocean floor is not a smooth plane. It contains canyons, ridges, and slopes. Without clear visual references, even a small navigational drift can cause a vehicle to lose orientation. In environments like the Challenger Deep, even sounding equipment becomes inconsistent. Pressure affects how sound travels. Sediment absorbs acoustic signals. The steep walls of trenches can redirect or scatter them. Mapping must be done slowly and carefully, often requiring multiple passes to verify data. Machines must move cautiously, because the seafloor can appear flat on sonar, even when it contains uneven features. Retrieving deep-sea vehicles presents its own set of technological limitations. Once a mission is complete, the vehicle must ascend. As pressure decreases, any trapped gases expand. Materials decompress. Systems must withstand the entire pressure gradient in reverse. This means the vehicle must be designed not only to survive the descent, but also the ascent. If something is damaged during the descent, the ascent may worsen the damage. A vehicle that cannot surface is lost permanently. Some autonomous deep-sea systems are designed to release ballast weights to help them rise, but this mechanism must work perfectly. If it fails, the vehicle stays on the seafloor, unreachable. The release system must function under pressure, operate without electrical failure, and withstand months or years without degrading if a long-term mission is planned. Adding redundancy helps, but each redundant mechanism increases weight, complexity, and potential failure points. Long-term installations on the seafloor, such as sensors or observatories, face different challenges. They must be built to operate without maintenance. Materials corrode slowly under constant exposure to seawater. Pressure stresses every component. Sediment can bury equipment. Microbial activity can affect structures. The lack of light and the cold reduce some forms of biological growth, but corrosion and mechanical wear continue steadily. Instruments must be able to measure conditions accurately for long periods without drifting out of calibration. Even the act of sending data from these installations to the surface becomes a technological challenge. Acoustic modems transmit data slowly. Large datasets cannot be sent in real time. Some instruments must store data internally, until researchers retrieve them months or years later. This delay slows scientific progress and increases the risk that something fails before the data is collected. These limitations don't reflect a lack of technological sophistication. Instead, they reflect the reality that technology built for human environments struggles when placed into an environment that doesn't share any of the conditions engineering normally considers. Machines are usually designed to operate in air, at moderate temperatures and under predictable forces. The deep ocean removes these assumptions, leaving only the fundamental physics of pressure, density, and limited energy. Even materials that perform well on land behave unpredictably here. Composites can delaminate, glass can fracture in unexpected patterns, metals can form micro cracks under repeated exposure to pressure cycles, plastics become brittle, insulation materials absorb water, adhesives weaken. The ocean applies its forces steadily and uniformly, and every material must respond correctly to those forces for the entire duration of the mission. The deeper the machine goes, the more every component must behave flawlessly. There are no options for improvised repairs. No divers can descend to perform maintenance. No tools can be deployed quickly. Recovery efforts, if possible at all, take many hours and carry significant risk. A system failure at depth usually means the permanent loss of the machine. This raises the stakes for every expedition, increasing cost, planning time, and engineering requirements. Because of this, even highly advanced nations with sophisticated research programs conduct relatively few missions to the deepest parts of the ocean. The engineering work required is costly and time-consuming. The risk of losing a vehicle is high, and the scientific payoff, while significant, does not always match the level of investment required for repeated exploration. This is not because scientists lack interest. It's because the environment forces technology into a corner where reliability becomes difficult to guarantee. When people imagine future technologies that might make deep-sea exploration easier, they often picture stronger materials, smarter robots, or better mapping systems. But the challenges of extreme depth won't vanish through incremental improvements. They require breakthroughs in material science, energy storage, communication, and autonomous navigation. The current limits reflect not a temporary gap, but a fundamental barrier that will take time and entirely new inventions to overcome. As we continue moving through this journey, the role of technology becomes clearer. It is not a tool that effortlessly adapts to any environment. It is a system built around the physical conditions humans evolved with. The deep does not share those conditions. It reshapes the rules. It forces technology to operate at its limits. And because of this, every attempt to explore the deepest places comes with challenges that define not only the mission, but the very edge of what our current engineering can manage. This is why technology trembles at the ocean's edge. Not because it fails easily, but because the environment demands perfection in conditions where perfection is difficult to maintain. These limitations continue shaping our understanding of the deep, guiding how we approach the world far below the surface as we move toward the next layers of this journey. As we keep descending, the difference between what machines can tolerate and what humans can endure becomes increasingly clear. Machines struggle here because physics leaves little room for error. Humans struggle because the environment removes every requirement our bodies depend on. It isn't a matter of courage or skill. It's biology set against conditions shaped by pressure, darkness, cold, and chemical balance. The deep doesn't resist human presence with aggression. It simply operates on terms that do not overlap with the conditions needed for human survival. When we talk about the fragility of humans in a world built to exclude us, we're describing the honest mismatch between what the deep requires and what human physiology can withstand. Even in shallow water, humans need protection. Our lungs rely on air at a very specific pressure. Our tissues depend on a balance of gases. We require warmth, light, moderate pressure, and access to oxygen. The moment one of these factors changes, the body reacts. At only a few meters underwater, divers must equalize the pressure in their ears to avoid discomfort or injury. At deeper levels, nitrogen dissolves into the bloodstream, leading to risks like nitrogen narcosis or decompression sickness. At depths of a few hundred meters, breathing ordinary air becomes impossible. Special gas mixtures help, but they have limits, and these limits appear long before approaching even a small fraction of the depth associated with the Challenger Deep. The Hadal Zone begins beyond 6,000 meters. No diver has ever approached anything remotely close to that depth, not because of a lack of interest, but because human physiology can't tolerate the pressure. At the pressure found in the Challenger Deep, the human body would collapse instantly. Bones would not hold shape, lungs would compress, blood vessels would rupture, every air-filled space would be crushed. But even describing it this way isn't a dramatic warning, it's simply a physical fact. There is no amount of training, discipline, or specialised breathing technique that could adjust a human body to these conditions. Even slight deviations from surface-level pressure cause significant distress. The pressure at depth is beyond any possible accommodation the body can make. This is why every dive to the deepest parts of the ocean requires a fully enclosed submersible with a pressure-resistant hull. Humans do not interact with the deep directly. They sit inside a metal sphere thick enough to resist external force. The sphere isolates them completely from the environment. It isn't a matter of preference, it's the only way to survive. The sphere must be sealed perfectly. It must have no seams, no weak points, no imperfections. It must maintain atmospheric pressure inside even while the outside experiences forces that could crush nearly any structure built by humans. Inside the submersible, the environment is controlled. Temperature, air composition, and pressure are kept stable. But this stability exists only because of the layers of engineering holding back forces that remain constant outside. The humans inside rely entirely on that engineering. Without it, survival is impossible. The fragility begins before they even reach the deep. Even during the descent, the sphere must counter increasing pressure. It creaks and flexes slightly under the force. Passengers hear these sounds and understand what they represent. It's not danger in the dramatic sense. It's the noise of material responding to physics. Life support systems must work perfectly. Oxygen must be stored safely. Carbon dioxide must be removed continuously. Filters must remain functional for the entire mission. Any failure in these systems becomes an emergency, because repairs cannot be performed outside the sphere. Divers cannot exit to fix anything. They cannot leave the protective shell. Every part of the life support chain must remain operational, and there is no backup environment available if something fails. This reliance on technology highlights why human presence in the deep is so fragile. When astronauts travel to space, they operate in an environment without pressure. While dangerous, that environment is mostly empty. A spacecraft provides air and maintains pressure. In the deep ocean, pressure is the opposite. Instead of emptiness, the environment is full of force. Instead of vacuum, there is crushing density. Instead of a lack of matter, there is water with immense weight pressing inward. The difference is significant because in space, a breach releases internal pressure outward. In the deep, a breach forces external pressure inward instantly. The consequences are immediate and irreversible. Even when everything works correctly, being inside a submersible at extreme depths requires psychological stability. The darkness outside eliminates all visual connection to the rest of the world. The sound of water pressing against the hull is constant. Space inside the sphere is tight. Movement is restricted. There is no room to stretch or walk. Humans evolved to navigate environments with open spaces, varied light, shifting temperatures, and breathable air. A deep-sea submersible removes all of these cues. There is no window large enough to provide a natural view. There are only small portals showing a narrow field of darkness, where light exists only when the lamps are turned on. The psychological effects aren't rooted in fear of monsters or danger. They come from the realization that the environment outside the hull is not survivable. Humans depend on the reliability of the sphere, the life support systems, and the guidance from the team at the surface. Every piece of equipment must perform correctly for hours during descent, for the time spent at depth, and during the long ascent. The ascent can be even more challenging because pressure decreases gradually, causing internal components to expand slightly. This expansion must be managed carefully. A malfunction during ascent is just as dangerous as one during descent. This dependency highlights a deeper reality. Humans cannot directly experience the deep environment. We cannot feel the water. We cannot breathe the air because there is none. We cannot touch the seafloor. We cannot hear the environment with our own ears. Every sense must be mediated through instruments. Cameras show what the eyes cannot see. Sonar maps what the ears cannot detect. Sensors reveal pressure, temperature, and chemical composition. Our understanding of the deep is filtered through technology that acts as an intermediary. Human presence becomes indirect. This indirect presence creates limitations in how much we can learn. An astronaut can collect samples with gloved hands. A diver can inspect an object directly. But in the deep ocean, the human occupant remains sealed away. All interaction must occur through mechanical arms controlled from inside the sphere. Those arms cannot replicate human dexterity. They operate at slower speeds, limited precision, and restricted angles. Sampling becomes slower and more deliberate. Mistakes are harder to correct. A sample lost or damaged cannot be retrieved again without repeating the entire descent. Even simple visibility is limited by the small size of the submersible windows. Cameras can provide more perspective, but they must rely on artificial lights that illuminate only small areas. Moving the vehicle changes the lighting angle, revealing new details but hiding others. Human presence is always contained within a tiny bubble of artificial conditions, surrounded by an environment that doesn't give feedback in the ways humans are used to interpreting. This creates a form of sensory disconnection. Observations become dependent on tools rather than direct experience. Another layer of fragility becomes clear when considering physical vulnerabilities. Humans must maintain a stable internal temperature, but the surrounding water is near freezing. The submersible must generate warmth and prevent the cold from reaching the interior. Insulation becomes critical. Electronics generate heat that must be managed. Ventilation systems ensure air circulation. If any of these systems fails, the interior environment can shift quickly. Even a drop in temperature of a few degrees becomes dangerous over time because the submersible has no alternative heat sources besides its own systems. Food and water supplies inside the submersible are limited. Most missions are designed to last only a few hours. Extending the mission increases risk because humans cannot remain inside indefinitely. Fatigue sets in. Concentration declines. Life support supplies dwindle. Even if everything else remains functional, time becomes a limiting factor because humans cannot wait long periods at depth for help if something goes wrong. Communication with the surface is another vulnerability. Acoustic signals travel slowly and can become distorted by surrounding terrain. Messages take time to reach their destination. Operators must anticipate delays. If communication is lost, the submersible must rely on pre-programmed procedures to surface. But those procedures assume that the systems remain functional. If something interferes with ballast release, propulsion, or navigation, the submersible could remain trapped at depth with no means to ascend. Machines can remain at a great depth indefinitely, but humans cannot. Even the journey itself introduces risk. Launching a submersible from a ship requires calm conditions. If the waves are too strong, deployment becomes unsafe. Recovery after ascent also depends on weather. Even if the submersible surfaces safely, the crew must wait until the support vessel can reach them. In rough seas, this wait becomes longer. Human survival at the surface remains dependent on external support after the journey through the deep environment. All these factors highlight how human fragility in the deep is not about dramatic dangers, but about a steady mismatch between biology and environmental conditions. The ocean at extreme depths exists in a form that doesn't accommodate human life. It doesn't adjust. It doesn't change. It doesn't offer even momentary conditions where humans can step out without protection. This is different from harsh environments on land. Humans can climb high mountains, cross deserts, and navigate frozen landscapes. Those places challenge but do not immediately destroy the body. The deep ocean, however, offers no buffer. Even in space, astronauts can perform spacewalks. They wear suits designed to provide everything their bodies need while floating in zero pressure. But the suits only need to resist outward force from internal pressure. The deep ocean requires resisting inward force at levels that cannot be balanced through wearable equipment. A suit that could survive at 10,000 meters would have to be a rigid metal container. The person inside would not be able to move. They would effectively be sitting in another submersible. This is why every human who has visited the Challenger Deep has done so inside a small pressure sphere. That sphere acts not as an exploration tool, but as a survival chamber. It preserves the conditions of the surface. Human presence becomes temporary and heavily mediated. It is an artificial intrusion into a world that does not accommodate human biology at any scale. As we keep sinking deeper in this journey, the differences between what humans can experience and what machines can tolerate become even clearer. The deep is not accessible on biological terms. It demands technological solutions for even the simplest interaction. And because those solutions must be perfect, human fragility becomes one of the central reasons why true exploration of the deep remains limited, guiding our understanding as we continue into the next part of this descent. When people talk about the deep ocean, especially its most extreme places, there's often a quiet assumption running in the background that it is a frontier waiting to be conquered, or a challenge waiting for someone bold enough to overcome it. That idea didn't appear suddenly. It grew gradually from centuries of exploration on land, where mountains could be climbed, deserts could be crossed, and remote regions eventually became understood, mapped, and transformed by human presence. The pattern gave people the impression that every unknown place on Earth simply needed the right combination of determination, tools, and time before its mysteries would yield. But the deep ocean does not fit into this pattern, and many misconceptions have grown from trying to force it into the familiar template of challenges humans have faced before. One common misconception is the idea that the deep ocean is simply difficult, not impossible, and that difficulty will eventually fade as technology advances. On land, difficult environments become manageable with better equipment. Cold climates become accessible through insulated clothing. High altitudes become tolerable with supplemental oxygen. Deserts can be crossed with vehicles and water supplies. People assume the deep ocean fits this same category, that with stronger materials, better robotics, or improved submersibles, the problem will disappear. But this belief does not account for the fact that the deep ocean's challenges aren't logistical barriers. They are physical realities that do not change regardless of intention or progress. The pressure at the bottom of the Challenger Deep is not something humans can gradually train for or adapt to. It is not a barrier that eases with practice. It is a fixed condition shaped by nearly 11 kilometers of water pressing downward. The idea of conquering such a place implies that it is resisting us, or that it is something to be overcome through effort. But the deep is not resisting. It is simply existing in a state defined by physics. The environment will not bend, it will not soften, it will not allow human presence without an artificial bubble of atmospheric pressure sealed inside layers of engineering. No accomplishment, no matter how impressive, changes the nature of the environment itself. Another misconception is the belief that the deep is empty and therefore simple in structure. When people imagine extreme depth, they often picture a vast dark emptiness, featureless, silent, and uniform. This leads to the idea that once a submersible reaches the bottom, exploration becomes a straightforward task. In reality, the terrain at the bottom can be complex. It contains slopes, cracks, ridges, soft sediment plains, and sudden variations shaped by tectonic processes. Mapping the seafloor is difficult even with modern sonar because sound behaves differently at extreme depths, and the signals must travel long distances through very dense water. Even calling the deep silent is a misconception. Sound travels extremely well in water, and the deep contains natural noises generated by shifting sediments, distant seismic events and biological activity. But humans inside a submersible cannot hear these sounds directly in a meaningful way because the hull blocks most acoustic cues. The environment may seem silent not because it is, but because the technology needed for human survival filters it out. In this way, even the silence people imagine is an illusion created by the protective layers that keep humans alive. There is also the idea that the deep can eventually become a routine destination, much like how air travel transformed the skies from unknown territory into a normal mode of transportation. Some assume that as submersibles become safer, cheaper, and more advanced, journeys to the deepest trenches will become accessible to more people. But this belief ignores how narrow the engineering tolerances are for surviving extreme pressure. A deep-sea submersible is not a vehicle that can tolerate minor issues. It is a precision-engineered life support chamber where every component must function perfectly. Routine travel requires forgiving conditions, where minor problems can be corrected without catastrophic failure. The deep offers no such margin. A small crack in a hull, a misaligned bolt, a single electronic failure, any of these can end a mission instantly. Routine use becomes impossible when every trip demands near-perfect construction, oversight, and operation. The deep will never become a place where hundreds of vehicles operate daily, because even one small mistake carries consequences that cannot be reversed. Another misconception is the belief that reaching the bottom once means we have conquered it. Historical narratives often frame the 1960 Trieste dive, or later expeditions like James Cameron's Descent, as proof that the deep is now reachable, and therefore conquered. But touching the bottom briefly does not mean the environment is conquered or understood. It means a single, carefully engineered machine managed to survive long enough to reach and return. This is a significant accomplishment, but it does not change the depth of our understanding or the limits imposed by physics. In many ways, deep-sea expeditions resemble brief visits to a distant world rather than steps toward occupation or regular travel. Spending a few minutes or hours at the bottom does not reveal everything that exists there. It does not make the environment accessible for future construction, habitation, or industry. It does not open the door for large-scale exploration. It simply shows that under ideal circumstances a vessel can survive long enough to take measurements and capture footage. The deep remains exactly as inaccessible after the expedition as it was before. Yet another misconception is imagining the deep as a place filled with dramatic danger. Giant creatures, sudden threats, supernatural stillness, or unpredictable forces waiting to consume anything that enters. This narrative comes partly from stories, partly from old seafaring myths, and partly from the human tendency to fill unknown places with imagined hazards. But the deep does not contain dramatic danger. Its challenges are steady and predictable. Pressure is constant, temperature is constant, darkness is constant. Nothing leaps out of the shadows, nothing attacks a submersible. The environment does not behave like a hostile creature. It is indifferent, shaped entirely by physics rather than intention. Thinking of the deep as dangerous in a mythic sense distracts from understanding the real challenges. People imagine great risks requiring bravery, as if an explorer might face sudden dangers that can be avoided through skill or intuition. But the deep cannot be navigated through instinct. It requires engineering, planning, and caution. The dangers are not dramatic. They're structural. They reside in pressure that crushes materials, darkness that hides terrain, and water so dense it defies familiar laws of perception. The deep is not a battlefield or a threat. It simply exists in a form incompatible with unprotected human presence. Another widespread misunderstanding is the belief that the deep ocean hides secret creatures or ancient structures that explorers might stumble upon, waiting in the dark. This belief comes from cultural traditions, stories, and the human imagination filling empty space with possibility. While the deep contains unusual and fascinating organisms, they are biological solutions to difficult conditions, not creatures waiting to challenge explorers. There are no ancient civilizations, no hidden ruins, and no vast mysteries of human history concealed beneath kilometres of water. The environment moves too slowly and remains too uniform for such structures to preserve. The reality is much quieter than the myths. The deep holds microbial life, fish, crustaceans, and soft-bodied organisms adapted to pressure and darkness, but it does not hide secrets in the dramatic sense. This misconception, while often harmless, shapes expectations. People imagine discoveries that change the world. They expect dramatic revelations, and when expeditions reveal instead a quiet landscape of sediment, small organisms and slow movement, some interpret that as a failure of exploration. But the deep is important not because it holds secrets in the mythic sense, but because it reveals how life adapts to extreme conditions, how Earth's systems function across enormous ranges, and how much of our planet remains outside direct human experience. Some misconceptions come from comparing the deep ocean to space. People imagine that if humans can travel to the moon, or send rovers to Mars, exploring the deep ocean should be simpler. After all, the deep is on Earth, accessible by boat, and only requires resisting pressure rather than navigating a vacuum. But this comparison overlooks key differences. Space has no pressure. Machines expand outward if they fail, but they do not collapse. The deep ocean contains immense pressure at every depth. Water is dense, causing drag and limiting movement. Communication is slower and more complicated. Visibility is restricted. Materials behave differently. While space travel brings its own challenges, the deep ocean is not simply an underwater version of space. It has unique physical constraints that technology cannot bypass easily. Another misconception arises from the belief that conquering means permanent access. When people think of conquering a mountain, they imagine climbers reaching the summit repeatedly. When people think of conquering a continent, they imagine establishing permanent presence. But in the deep ocean, no human presence remains after the expedition ends. Nothing is built, nothing stays. No equipment remains active for years without constant maintenance. There are no settlements, bases, or outposts. The deep returns to its normal state immediately after each mission. Nothing of human presence remains besides collected data. In this sense, the deep has not been conquered. It has been visited briefly. Another common misconception involves underestimating the complexity of retrieving samples from the deep. People imagine that scientists can lower a container, collect some sediment or organisms, and bring them back easily. But pressure changes alter the samples. Biological specimens often die upon ascent. Chemical compositions shift, sediments reorganize. The very act of removing something from its environment changes it. Many organisms adapted to pressure collapse or deform when exposed to surface conditions. This limits the ability to study the deep using traditional methods. Some samples can only be analysed at depth using instruments placed directly on the seafloor. The idea that the deep is simply waiting for us to gather its resources is another misconception. People sometimes imagine rare metals, minerals, or unknown materials lying untouched on the seafloor, waiting to be collected. But extracting resources from extreme depths is not straightforward. Machines capable of excavating must survive pressure, cold, and darkness. They must be extremely reliable. They must operate with precision to avoid disturbing fragile ecosystems. And even if a machine could extract resources, transporting them upward introduces challenges. Weight becomes a factor. Temperature changes affect materials. Pressure changes alter physical structures. Resource extraction at this depth is not simply difficult, it may be impractical. Some also assume that deep-sea exploration can be expanded quickly if enough interest or funding appears. But expertise in deep-sea engineering is rare. Manufacturing pressure-resistant vehicles requires specialised facilities, materials, and knowledge held by only a few organisations in the world. Scaling such efforts requires years of development, testing, and refinement. The deep is not waiting to be opened by ambition alone. Another misconception is that once technology advances, The deep will become a place humans can explore freely, even without submersibles. This stems from imagining suits that could withstand pressure or technologies that could counteract environmental effects. But a suit built to resist the pressure at 10,000 meters would need to be thick, rigid, and heavy. The person inside would not be able to move. It would function more like a portable pressure hull than a suit. Moving inside it would require powered systems, and even if such a suit existed, controlling it in dense water without visibility would be nearly impossible. While powered exosuits operate in shallower depths, extending them into the Hadal zone is not realistic with current or near-future materials. The myth of conquering also fails to consider the cost of each expedition. Engineering, manufacturing, transportation, and recovery all require substantial resources. A single deep dive involves months of preparation, extensive safety checks, and teams of engineers monitoring every detail. The deep is not a place where continual presence makes sense given the effort required for each visit. Some misconceptions grow from misunderstanding the term exploration. People imagine exploration as mapping, documenting, and establishing a consistent presence. But in the deep, exploration more closely resembles sampling. A small area is examined for a short time, a limited set of data is gathered, then the mission ends. The environment is too vast and hostile for continuous mapping in the traditional sense. Even modern sonar cannot cover the entire trench in detail without decades of work. Mapping the deep is a slow process, not because of lack of interest, but because of the constraints imposed by the environment. These misconceptions shape the way people talk about the deep ocean, but understanding the real limits helps clarify why the deepest areas remain among the least explored places on the planet. The deep is not an adversary. It is not a frontier waiting for conquest. It is a stable, unchanging part of Earth that exists outside human conditions. Efforts to explore it must work within its rules, not impose new ones. As we continue this descent, each layer of understanding becomes clearer. The misconceptions fade as the physical realities sharpen, and these realities guide how we continue exploring the world far below, setting the stage for the next part of this journey. Reaching the very bottom of the ocean has happened so rarely that each successful descent stands almost alone in history, separated by decades, shaped by different motivations, and carried out with different technologies. These attempts were never routine, never predictable, and never guaranteed to succeed. Each was the result of years of planning, careful engineering, and a willingness to trust a machine built to enter an environment that offers no margin for mistakes. When we look at the few times humans and their instruments have reached the Challenger Deep, the first thing that becomes clear is how infrequently this kind of exploration has been possible, and how much effort was required for every moment spent on the seafloor. The earliest and perhaps most famous expedition took place in 1960 with the bathyscaphe Trieste. The Trieste was unlike anything used before. Its design came from a period when deep-sea engineering was still new, and solutions often relied on creative combinations of materials rather than advanced composites or precision robotics. The vessel was composed of two main parts: a large float filled with gasoline for buoyancy, and a thick steel sphere suspended underneath it. The float provided the upward force. The sphere provided the safety. Gasoline is less dense than water and compresses less than air, which allowed it to maintain buoyancy at depth. The sphere, made from thick steel plates, was engineered to withstand the pressure at nearly 11 kilometers below the surface. Inside that steel sphere sat Don Walsh and Jacques Picard. During their descent, the environment gradually changed from bright surface light to complete darkness. They heard the hull creak under the increasing pressure, a normal but sobering reminder of the forces pressing in around them. The descent took hours. There were no high-resolution screens, no digital sensors, no advanced communication systems. They relied on simple instruments, portholes, and basic electrical equipment. The windows were made of plexiglass shaped into thick cones. At shallower depths, they remained clear. But as the pressure rose, the windows began to deform slightly. The plexiglass became cloudy. Light bent differently through the material. Vision became limited. The final portion of their descent introduced one of the earliest examples of how unpredictable the deep ocean can be. Near the bottom, they heard a loud crack. The noise came from one of the outer plexiglass windows. It did not break completely, but the sound signalled that the material had reached the limits of what it could tolerate. Despite this, the Trieste continued downward until it finally touched the seafloor. The crew saw a landscape of sediment disturbed by their arrival. Visibility was poor because the landing stirred a cloud of fine particles. They remained for only a short time, long enough to observe their surroundings, confirm the depth, and collect limited data. Then they began the long ascent, returning to the surface with the knowledge that humans had touched the deepest point on Earth for the first time. For decades afterward, no crewed mission attempted the same descent. The Trieste dive demonstrated that reaching the bottom was possible, but it also showed how narrow the safety margins were. The engineering challenges remained enormous. Material strong enough to withstand the pressure at depth had not advanced enough to make repeated crewed dives more feasible, and the scientific value of sending humans rather than instruments did not outweigh the risks and costs. While numerous unmanned probes and remotely operated vehicles explored parts of the deep ocean, few were designed to survive the full depth of the Challenger deep. In the 1990s, the Japanese unmanned research vehicle Kaiko became one of the few machines capable of reaching the full depth repeatedly. Kaiko conducted dozens of dives, collecting valuable data, images, and samples from the Hadal zone. It helped map portions of the seafloor and retrieve organisms living under extreme pressure. Because it carried no humans, its design could prioritize survival of the machine rather than the safety of occupants. This allowed it to operate more freely, though still within the limits imposed by pressure and temperature. Kaiko became one of the most productive deep-sea explorers of its time, but it was lost at sea in 2003 when a support cable broke during a storm. Losing such a rare and capable vehicle highlighted not only the difficulty of deep-sea exploration, but also the fragile nature of the equipment used to access it. Around the same period, other unmanned systems attempted to reach extreme depths. Some succeeded briefly, others failed during testing or descent. The environment remained a constant challenge. Electronics needed protection, flotation materials needed improvement, pressure housings needed careful engineering. Every machine that touched the bottom did so with the understanding that any failure during descent or ascent would leave it permanently lost in a place beyond recovery. Human beings did not return to the Challenger Deep until 2012, more than 50 years after the Trieste dive. This time, the mission was carried out by the Deep Sea Challenger, a submersible designed by James Cameron. Unlike the large, gasoline-filled float of the Trieste, this vehicle used advanced syntactic foam for buoyancy and a streamlined vertical shape that allowed it to descend faster and maneuver more effectively near the bottom. The sphere holding the pilot was made from specially forged materials and designed to withstand the full external pressure. The Deep Sea Challenger's mission emphasized how technology had evolved. Cameras provided high-definition footage. Mechanical arms collected sediment samples. Sensors recorded temperature, pressure, and other environmental data. Despite these advancements, the mission still faced significant risk. The descent took hours. The exterior lights illuminated only a small region of the environment. Sediment clouds appeared whenever the vehicle approached the seafloor. Communication with the surface relied on acoustic signals. The pilot had limited mobility inside the cramped pressure sphere. Cameron's dive showed what modern engineering could achieve. He spent more time at the bottom than the Trieste crew and collected more data. But the mission also reinforced the reality that even advanced technology does not make the deep ocean routine. After the expedition, the Deep Sea Challenger was transported across the country and sustained significant damage during a truck fire, ending its active use. This incident had nothing to do with the deep itself, but it highlighted the vulnerabilities of unique research vehicles. When a machine that rare is lost or damaged, replacing it becomes difficult because of the resources required to build it in the first place. Between 2012 and the late 2010s, additional unmanned systems attempted dives to the Hadal Zone. Some used new materials, others used improved buoyancy systems, yet each mission remained an event requiring careful planning rather than a standard procedure. No automated system existed that could survey the deep regularly. No network of deep-sea vehicles operated on a schedule. Each dive represented a concentrated effort from researchers, engineers, and support crews. The next major shift came with the development of the limiting factor, a submersible built by Triton submarines and used by explorer Victor Vescovo. This vehicle was engineered specifically for repeated dives to full ocean depth. Its titanium sphere was forged from multiple pieces bonded in a way that produced a uniform structure without weak points. Its flotation system relied on improved syntactic foam. Its electrical and mechanical systems were designed for reliability under extreme pressure. These improvements allowed the limiting factor to conduct multiple dives to the Challenger Deep across several expeditions. The limiting factor's design aimed for repeatability rather than a single descent. This was new in the history of deep diving. Previous crewed missions reached the bottom only once or only a few times, limited by engineering constraints or cost. The limiting factor attempted to change that pattern by providing a platform for scientific research that could, in theory, visit the trench repeatedly. And for several years it succeeded. Vescovo and various scientists descended multiple times, collecting samples, recording footage, and exploring regions of the seafloor that had never been seen before. Even so, each dive required extensive preparation. Each ascent and descent demanded careful monitoring. The submersible systems needed constant inspection and maintenance. Its support ship, the DSSV Pressure Drop, carried specialized equipment for launch, recovery, and communication. These missions demonstrated that with enough expertise and resources, reaching the bottom could happen more than once. But they also showed how rare such capabilities are. Only one vehicle in the world was able to perform these tasks consistently. No other organizations possessed a comparable platform. Unmanned vehicles continued to contribute during this period as well. Various research groups deployed autonomous landers that sank to the bottom, recorded data, and then released weights to ascend. These landers provided valuable information about sediment composition, deep-sea organisms, and chemical environments. Some carried cameras that captured images of snailfish and amphipods feeding near baited traps. While these systems lacked maneuverability, they were affordable enough to risk losing, which made them useful for wide-area sampling. Despite these efforts, the number of successful expeditions remains very small compared to the vastness of Earth's oceans. The Challenger Deep has been visited fewer times than the Moon. Each visit provides new insights, but none of them reveal the entirety of the environment. The trench is large, with multiple basins separated by ridges and slopes. Each basin contains unique terrain and ecological features. Mapping them fully would require hundreds of dives, each demanding the same level of preparation and caution as the few we have seen. Another factor that limits these expeditions is cost. Deep-sea technology requires specialized materials, manufacturing techniques, testing procedures, and logistics. Every component must be engineered to exacting standards. The construction of a deep-rated submersible can take years. Operating it requires a dedicated support vessel, a trained crew, and a team of engineers familiar with systems that cannot be found in everyday manufacturing. Funding such operations is difficult because the scientific community must balance the value of data collected at extreme depth against the cost of reaching it. Even when funding is available, safety remains a priority. After incidents involving submersible failures elsewhere, the importance of rigorous testing has become even more apparent. Dives to the deepest points must involve equipment that has been tested repeatedly, inspected carefully, and proven reliable. There is no room for improvisation or shortcuts. This limits the number of organizations capable of such work. As new technologies emerge, additional expeditions may become possible. Advances in autonomous systems may allow long-term monitoring of the seafloor. Improved battery technologies might extend dive times. New materials may make construction easier or more reliable. But even with these advancements, the deep will remain a place where only a small number of machines can operate safely. Each expedition will continue to carry weight because the challenges cannot be removed through incremental improvement alone. What these rare expeditions show most clearly is that reaching the bottom is not the same as understanding it. A few brief visits cannot replace continuous exploration. The deep does not yield information quickly. It must be studied through repeated observations, careful sampling and long-term monitoring. And each of these requires returning again and again to an environment that resists sustained presence. As we continue through this long descent, the significance of these missions becomes clearer. They represent more than technological milestones. They show the limits of human and mechanical endurance. They highlight how reaching the bottom is both an extraordinary achievement and a reminder of how much remains beyond our reach. And this understanding sets the stage for the questions that linger about what we still cannot know as we move into the next part of this journey. As we continue drifting through this long descent, the closer we come to the bottom, the clearer it becomes that the Challenger Deep is not simply an extreme environment we've barely explored. It's also a place that raises questions we don't yet have the means to answer, questions that persist even after decades of engineering efforts, scientific missions and rare descents to the seafloor. Every new measurement, camera observation, or sample retrieved from these depths answers something small while opening a new set of uncertainties. None of these unknowns feel mysterious in the dramatic sense. They aren't shaped by legends or hidden threats. They're shaped by the limits of technology, the complexity of Earth's geology, and the slow, subtle processes that unfold under conditions far removed from anything at the surface. One of the most persistent questions concerns the exact shape and structure of the seafloor within the trench. Maps exist, but they don't offer the same level of clarity we have for landscapes on land, or even for much of the shallow ocean. The deepest points of the Challenger Deep contain multiple narrow basins, steep slopes, and irregular features shaped by tectonic forces. While sonar mapping has produced general outlines, details remain incomplete. At these depths, sonar signals weaken, scatter, and distort. A small misreading could mean a difference of tens of meters, and when discussing the deepest point on Earth, tens of meters matter. Researchers still debate which basin is truly the deepest because slight variations in measurement can shift rankings. Not because anyone doubts the existence of the trench, but because achieving centimetre-level precision at nearly 11 kilometres underwater remains a challenge. Another major question involves the long-term geological activity in the trench. The Challenger Deep sits at a convergent plate boundary where the Pacific Plate sinks beneath the Philippine Sea Plate. This process, known as subduction, drives much of the Earth's geological cycling, but the details of how sediments move, compact and deform at these depths are still unclear. Instruments placed at extreme depth can measure some of the slow shifts, but placing those instruments requires expensive expeditions, and recovering them requires another full descent. Data often cover short periods, months or years rather than decades. This limits our understanding of long-term trends. For example, we still don't know precisely how sediment layers shift after earthquakes, or how quickly biological material accumulates on the seafloor over large timescales. Another set of questions revolves around the chemical environment at the bottom. Deep-sea sediments contain compounds shaped by pressure, temperature, microbial activity, and the slow accumulation of material from the surface. But retrieving samples without altering their chemical state is difficult. Pressure-sensitive compounds may change structure on ascent. Gases trapped within sediments may escape. Microbial community adapted to extreme pressure may die before reaching the surface. Scientists have built pressure-retaining containers to preserve samples, but these are complex tools that can only hold limited quantities. This means that many chemical and biological processes in the Hadal zone remain only partially understood. We can identify major components, but the fine details, how certain reactions proceed, how nutrients cycle, how microbial communities interact, remain unresolved. One of the biggest unanswered questions concerns the full diversity of life in the trench. The small number of dives has revealed only a fraction of the organisms living at depth. Cameras capture amphipods, snailfish, holothurians, and microbial mats, but these represent a tiny sample. Many species likely remain undiscovered. Biological exploration requires repeated visits across different areas, seasons and depths within the trench. Because dives are rare, each one offers just a brief snapshot of life, not a continuous record. There may be organisms living in narrow pockets of the trench that have never been observed. Some may rely on chemical gradients or geological features that only occur in isolated sections. Without more frequent exploration, those species remain unknown. Even for the species we have documented, important questions remain about how they survive. For example, snailfish exist near the theoretical limit of vertebrate pressure tolerance. The deeper they live, the more pressure affects cellular structures and proteins. Researchers have identified certain compounds that help stabilize proteins under pressure, but the exact combinations and mechanisms in some species remain unclear. We still don't know whether there is a precise depth beyond which no vertebrate can survive, or whether some species have adaptations we have yet to identify. Microbial communities present even more unknowns. Many of these organisms thrive in conditions that challenge basic assumptions about biology. Some live on chemical energy sources unavailable at the surface. Others survive at pressures that would destabilize the membranes and proteins in most known organisms. Understanding these adaptations requires more samples than we currently possess. Another question concerns the movement of nutrients in and out of the trench. Some organisms feed on marine snow, while others rely on occasional large food falls, such as the carcass of a whale or large fish. But researchers still don't know how often such events occur, or how long their effects last. A large food fall might support a community for months or years, but because deep-sea expeditions capture only brief glimpses, it's difficult to estimate how common these events are, or how they shape long-term ecological dynamics. Without continuous monitoring, the broader pattern remains unclear. A separate but equally important question involves the physical behavior of water at extreme depths. The deep ocean experiences slow movements of water masses, driven by global circulation patterns. But circulation at Hadal depth is not well understood. It may vary seasonally or over longer cycles. It may influence nutrient distribution, sediment transport, or microbial activity. But measuring these slow movements requires instruments that can survive at depth for long periods while transmitting data reliably. Only a few such instruments exist, and deploying them requires major expeditions. This leaves gaps in our knowledge of how water circulates within the trench, and how those movements influence the environment. The tectonic forces shaping the trench also raise questions scientists cannot fully answer. Subduction zones generate earthquakes, but the relationships between deep-sea seismic activity and physical changes in the trench floor are only partly understood. Some earthquakes may shift sediment layers subtly, others may trigger landslides within the trench. But without long-term monitoring devices positioned at depth, the exact impact of seismic events remains difficult to track. Researchers can record the vibrations from distant instruments or measure changes after the fact, but the real-time processes remain hidden. Even the exact maximum depth of the Challenger Deep remains subject to small variations depending on measurement technique, equipment calibration, and environmental conditions. Water density changes with temperature and salinity, both of which can influence the speed of sound and therefore affect sonar measurements. Pressure sensors provide more direct readings, but must be calibrated precisely. Small differences in calibration produce small differences in measured depth. Over decades, multiple expeditions have produced values clustered within a narrow range. but pinpointing an exact number remains surprisingly difficult. The deep does not hide this information intentionally. The challenge lies in measuring it under extreme conditions. Another important question concerns long-term changes in the trench, driven by climate or ocean conditions. Most oceanographic data comes from shallower regions, where changes in temperature, circulation, and chemistry are easier to detect. But how these surface or mid-ocean changes propagate into the Hadal zone remains uncertain. Some researchers believe deep waters mix slowly and therefore respond to surface changes on long timescales, perhaps centuries. Others suggest that certain pathways allow deep waters to be replaced more often. Because long-term data sets from extreme depths are rare, the response of the trench to broader climate trends remains difficult to determine. The role of deep trenches in carbon cycling is another open question. Sediments at extreme depth accumulate organic carbon over long timescales. Microbial communities may break down this material slowly, but the rate at which carbon becomes locked into sediments versus recycled into the ocean remains uncertain. This affects global carbon models and our understanding of Earth's natural carbon storage. Some studies suggest trenches may act as long-term carbon sinks. Others propose more complex interactions. Without continuous sampling, the dynamics remain unclear. There are also questions about the physical properties of sediment under extreme pressure. Laboratory tests mimic some conditions, but real sediment behaves differently when influenced by local chemical gradients and long-term compaction. The seafloor in the trench may behave like a soft surface or a firm one depending on composition. Some areas might be stable, while others may shift easily under disturbances. Because submersibles must land carefully, understanding sediment behavior is important, yet still incomplete. Another area of uncertainty involves deep-sea currents, carrying small organisms, larvae, or dissolved chemicals from one part of the ocean to another. While surface currents are well mapped, the pathways at extreme depth remain unknown. Organisms found in the Challenger Deep may have originated elsewhere. Others may be isolated with limited exchange between basins, but without biological markers or long-term sampling, these relationships remain speculative. Questions also persist about the long-term stability of the trench walls. Some slopes appear smooth, while others show fractures and irregularities. These features may shift slowly over time. Landslides can occur when sediment destabilizes, but the rate and frequency of such events are not well understood. They could reshape the environment in ways that influence biological communities, chemical gradients, or depth profiles. But because few expeditions revisit the same area repeatedly, detecting these changes becomes difficult. Another question, often overlooked, involves sound at Hadal depth. Researchers have recorded unusual acoustic signals in deep trenches, long, low-frequency sounds that travel considerable distances. Some originate from marine life, others from seismic activity, and others remain unidentified. These sounds aren't mysterious in the supernatural sense, but they raise questions about how organisms communicate at depth, and how geological or hydrodynamic processes generate acoustic energy. Without detailed acoustic surveys, identifying the sources of these sounds remains difficult. Even basic questions about the temperature distribution at depth hold uncertainties. While the deep ocean is near freezing, small variations may occur due to water movement or chemical reactions in sediment. These variations might influence biological activity or sediment processes, but detecting such changes requires highly sensitive instruments placed directly on the seafloor for long durations. There are also unresolved questions about the long-term effects of human presence in the deep. While human impact on the Hadal zone is currently minimal, plastics and pollutants have been found even in the deepest trenches. How these materials reach such depths, how long they persist, and how they affect deep-sea organisms remain open areas of study. Microplastic fibers have been found in amphipods. Chemical pollutants have been detected in sediment. These findings raise questions about how human activity at the surface influences environments thought to be insulated from direct impact. Another question concerns whether human exploration should increase. Scientists debate how often deep-sea expeditions should occur, balancing the desire for knowledge with respect for fragile ecosystems. Some argue that increasing the frequency of unmanned dives is beneficial. Others suggest that too much disturbance, even from careful missions, could alter delicate habitats. Because the deep is so rarely visited, we don't yet know how sensitive some regions may be. Finally, one of the most fundamental questions is simply how much of the trench remains unseen. The area is vast, only narrow slices have been filmed, only small patches of sediment have been sampled. The deep is too large and too inaccessible to survey fully with current technology. Every expedition provides details from only a limited area. The rest remains unexamined not because it holds secrets intentionally, but because physically reaching it remains so difficult. As we continue along this downward journey, these unresolved questions show how much of the deep remains outside our direct understanding. They don't point toward hidden dangers or dramatic revelations. They simply remind us that some environments take far longer to understand than others, especially when every measurement and sample must be filtered through layers of engineering designed to protect humans and equipment from conditions that do not support our presence. And these questions continue guiding how we approach the ocean's deepest regions as we move toward the final part of this exploration. As we continue moving through this long descent, and as every layer of the deep has unfolded through pressure, darkness, and slow geological shaping, the awareness settles in that places like the Challenger Deep cannot be approached with the same expectations we bring to other environments. They cannot be mapped easily, visited often, or understood quickly. They cannot be changed to fit our comfort or routines. They exist in a form that does not accommodate human presence, and yet they continue operating quietly, stable across timescales that stretch far beyond anything familiar at the surface. The longer one thinks about this, the clearer it becomes that the deepest places are not environments we are meant to claim in any practical sense. They are environments we study carefully, visit rarely, and learn from slowly. This does not diminish their importance. In fact, it reinforces why they matter. The deep represents one of the few parts of Earth that remain mostly insulated from human activity. Its conditions have not shifted because of development, industry, or settlement. Its ecosystems have evolved in relative isolation. Its geology continues without interference. The sediment layers record history over long timescales. Its biological communities navigate a world whose rules are shaped not by surface-level conditions, but by pressure, cold, and the slow movement of nutrients. Observing this environment provides insight into how life and geological systems operate when all familiar variables are removed. As researchers explore the deep, one theme becomes consistent. The more they uncover, the more they recognize how much remains unknown. The aim is not to extract resources, build structures, or establish permanent presence. The aim is to observe, record, and understand. The deep does not offer a path for expansion or habitation. It offers a path for study. And the difference between those two goals shapes how humans approach the environment. Observing does not require altering the surroundings. It requires tools that interact with minimal disturbance, instruments that leave no long-term footprint, and careful planning that respects limits rather than attempting to bypass them. Each descent into the Hadal Zone reinforces this mindset. Every submersible, lander, or probe enters the water with the understanding that the environment does not provide second chances. A miscalculation does not result in inconvenience, it results in loss. This reality encourages caution, but it also encourages precision. When machines reach the bottom successfully, the opportunity to gather data carries weight because so few opportunities exist. The data collected is often modest in appearance. Sediment samples, temperature readings, pressure logs, footage of organisms drifting across the seafloor, but each small piece contributes to a larger picture that can only be assembled through many separate efforts. Thinking about the deep in this way changes the perspective from conquest to participation. Humans are not imposing themselves on the trench. They are interacting with it briefly, carefully, and with the understanding that their tools are temporary visitors. The environment does not require anything from us, and it continues operating whether or not we observe it. This encourages an approach built on respect for the physical boundaries that define the Hadal world. Respect does not mean reverence in the emotional sense. It means acknowledging the realities of pressure, darkness, energy limitations, and the fragility of human presence. When scientists describe their experiences at depth, their accounts do not emphasize control or mastery. They emphasize how narrow the limits are, how sharply defined the safe parameters remain, and how the environment determines nearly every decision made throughout the descent. They describe the long preparation that comes before each mission, the detailed testing of every component, and the fact that the environment always has the final say in whether the mission succeeds. There is no sense of ownership because ownership is not compatible with the nature of the deep. Control in this environment is an illusion. The only thing humans control is how carefully they prepare. This perspective carries into the scientific process. When samples are retrieved, they are studied not as trophies, but as evidence. The goal is to understand the chemical signatures in the sediment, the adaptations in the organisms, the structural properties of materials under pressure, or the geological formations that tell a long-term story of the trench. Each sample represents a moment where the deep allowed a small fragment of itself to be examined, but the context of that fragment remains tied to an environment we cannot directly inhabit or observe continuously. The difficulty of deep-sea research also sets limits on how quickly knowledge accumulates. On land, scientists can revisit the same site multiple times in a year. They can set up long-term instruments, monitor changes, and refine their understanding through repeated experiments. In the deep, repetition is rare. Instruments cannot be checked frequently. Submersibles cannot descend on short notice. Weather at the surface can delay missions. Technical issues can postpone expeditions for years. Because of this, each visit becomes part of a slow, ongoing effort where progress is measured not by rapid breakthroughs, but by steady accumulation of small insights. This slow pace encourages patience, and patience in turn encourages a form of humility. Not the emotional kind, but the practical kind that recognizes how Earth contains environments operating on scales and conditions that do not align with human expectations. The deepest places exist independently of human history. They do not reflect cultural memory. They do not respond to human activity except in the most indirect ways. Their ecosystems evolve without human observation. Their geology unfolds at its own pace. When humans enter that environment, they are stepping into a world that does not revolve around them in any way. At the same time, the deep is connected to the rest of the planet through processes that link surface and sea floor. Organic material drifts down from above. Tectonic forces shape landscapes far beyond the trench. Cold water circulates slowly, interacting with global currents. These connections remind us that while the deep may be physically separate, it is not isolated from the overall functioning of Earth. Observing the trench provides a view into how Earth operates across different layers, not as separate systems, but as interdependent ones. Understanding the trench also requires acknowledging the limits of what we can construct. Technology can create pressure-resistant spheres, high-energy lights, robust syntactic foam, and resilient electronics. But even with these advancements, our machines remain temporary guests. They require maintenance, monitoring, and support vessels at the surface. They cannot operate continuously without human guidance. They cannot remain indefinitely in the deep without degradation. This reality reinforces the fact that the deep ocean is not waiting to be integrated into human systems. It exists within Earth's systems, and our role is to learn from it without assuming that access is permanent or straightforward. As new expeditions take place, they add detail to the larger picture. Some reveal new organisms, others map small portions of the seafloor. Some record sounds or collect water samples that show unseen chemical processes. Each piece fits into a structure that grows slowly over time. The rate of discovery reflects the challenges built into the environment. Observations must be pieced together like fragments of a long, complex record. The deep does not provide wide, accessible views. It offers narrow windows, short visits, and limited opportunities for sampling. But these small opportunities carry value because of how rare they are. Thinking about the trench as something to observe rather than something to own or control allows exploration to proceed with clarity. Observation emphasizes accuracy. It demands planning. It respects the constraints of engineering. It encourages responsible decision-making. In this sense, observing the deep is not passive. It is an active effort to understand an environment while acknowledging the boundaries of our role within it. This view also helps place deep-sea exploration within the broader context of scientific research. In many scientific fields, progress is measured through large data sets, frequent experiments, or rapid iteration. Deep-sea research cannot follow that model. Instead, it follows a path shaped by patience and precision, where progress occurs in small increments. Each increment reflects hours of preparation, significant investment, and careful analysis. The value lies not in volume but in reliability. Thinking about the deep in this way aligns with the way geologists, oceanographers, and biologists often describe their work. They talk not about conquest but about observation, not about ownership but about understanding, not about certainty but about the steady reduction of uncertainty through careful study. This approach does not diminish the importance of the deep. It highlights its role as one of Earth's last environments where human presence remains temporary and heavily mediated. The deeper this perspective sinks in, the clearer it becomes that the deep will remain a place defined by its own terms. It will continue to operate under pressure and darkness regardless of how much technology advances. Its ecosystems will continue adapting slowly. Its geological features will change over long timescales. Observation will always require tools designed with extreme precision, and human presence will always depend on engineering that isolates life from an environment that cannot support it. As we drift through the final portion of this long exploration, the sense that emerges is not one of finality or closure. It's simply an understanding that the deep remains accessible only in narrow windows and brief visits. It offers insight without granting control. It reveals small pieces without offering full access. This balance shapes the way the trench is studied and the way future expeditions will unfold. It sets the tone for how humans interact with environments that operate outside the conditions that define everyday life at the surface. The Challenger Deep continues existing in a steady, self-contained state, shaped by forces unchanged by human exploration. Each journey to its floor represents a moment where human engineering meets an environment built on different principles, and each moment adds something small to our understanding of a place that does not need us, yet still teaches us through the fragments we are able to gather. The descent ends, but the environment continues unchanged, leaving room for future research to build slowly on the work done so far, forming a long, careful record of a world observed from the edge of what our tools and our presence can withstand.